Welcome, wherever you are right now, perhaps lying in bed, perhaps winding down after a long day. This space is for you. Take a moment to get comfortable, adjust your pillow, and let your body rest. You don't need to do anything but listen. Let the sound of these words guide you gently toward relaxation and sleep. Tonight, we're going to drift into a journey together, not across the stars, but down into the vast and hidden world beneath our oceans. A world that covers more than 70% of our planet, yet remains mostly unseen. You've probably heard the phrase, "We know more about the surface of the moon than the bottom of our oceans." Strangely enough, it's true. Out of all that endless blue, out of all that mystery stretching beneath the waves, humanity has only managed to explore about 5%. Just 5. Why is that? Why, in an age of satellites, rockets, and artificial intelligence, do the oceans remain such a dark, uncharted frontier? What secrets lie beyond the edge of our knowledge in the crushing depths? In the darkness, where strange creatures glow, in the silent plains at the bottom of the sea. Over the next few hours, we'll travel through science, history, philosophy, and imagination. We'll uncover why the oceans are so difficult to explore, what mysteries may still be waiting, and why this hidden world matters so deeply to our future. So close your eyes if you wish. Allow yourself to breathe slowly, deeply, and evenly. Let each breath carry you further into calmness. You don't need to remember everything I say. You don't need to follow every detail. Just let the rhythm of the words hold you. Let curiosity and relaxation guide you at the same time. And now, you will begin with the oldest mystery of all, the ocean itself. The ocean has always been a mirror for the human imagination. From the very first moment people stood on the shore and looked out at the horizon, there was a sense of wonder and unease. That endless stretch of water seemed both inviting and threatening. It promised food, travel, and discovery, but it also hid dangers, storms, unseen currents, and creatures that no one had ever laid eyes on. For much of human history, the ocean was less a known place and more a symbol of mystery, of the unknown, of the infinite. Even today, with satellites orbiting above and submarines diving below, that sense of mystery hasn't gone away. In fact, it has only deepened, because the more we learn about the sea, the more we realize how little we truly understand. Every time a remotely operated vehicle descends into the abyss, every time a new expedition maps a seamount or trench, something unexpected emerges. A new species, a strange geological formation, a chemical process never seen before. It's as if the ocean is reminding us, you have only scratched the surface. But let's slow down. Before we dive into technology and science, let's rest for a moment in the feeling of that mystery. Imagine yourself standing at the shore of the ocean at night. The waves rise and fall in a rhythm older than human memory. The air is heavy with salt. The horizon blends into the darkness so that sea and sky seem to be one, somewhere far below. The surface, in places no sunlight ever touches. There are mountain ranges taller than the Himalayas and trenches deeper than Mount Everest is tall. There are plains, volcanoes, rivers of superheated water spilling out of the earth itself. There are forests of coral, alive with creatures glowing like stars, and yet you can't see any of it. From where you stand, the ocean seems calm, almost simple, just a surface, just a skin. This is the essence of the mystery. That something so vast, so vital to life on Earth, can remain invisible. Why is it that only 5% of this world has been explored? One reason is scale. The ocean is unimaginably large. It covers more than 361 million square kilometers. Its average depth is about 3.7 kilometers. At its deepest point, the Mariana Trench plunges nearly 11 kilometers down. To put that in perspective, if you dropped Mount Everest into the ocean, it would disappear beneath the waves, with more than 2 kilometers of water still above its peak. Exploring such a space isn't like hiking across land. It's like trying to enter another planet. Another reason is that the ocean doesn't reveal itself easily. Unlike outer space, where we can look up and see the stars, the ocean hides behind a barrier, the surface. Once you dive down just a few dozen meters, sunlight fades. Beyond 200 meters, there is almost no light at all. The deep ocean is a realm of perpetual night. To explore it, we need lights, machines, and technology just to see what's in front of us. But the mystery of the ocean is not only scientific, it's also psychological. For centuries, cultures around the world have filled the unknown sea with myths and legends. In Greek stories, the ocean was the domain of Poseidon, god of earthquakes and storms. In Norse mythology, a great serpent encircled the world beneath the waves. In Polynesian traditions, the ocean was alive with spirits, both helpful and dangerous. These stories were not just fantasy. They were reflections of a truth. People sensed that the sea contained more than they could comprehend. Even now, our minds are drawn to this mystery. Think of how often the ocean appears in dreams, in stories, in movies. It is both peaceful and terrifying. A place of beauty and danger. A place where the rules of our everyday world no longer apply. That's why the fact that we've explored so little of it continues to fascinate us. It's not only about the science, it's about what the unknown does to our imagination. So as we begin this journey, let yourself lean into that feeling. The ocean is not just water. It is not just a resource or a map to be filled in. It is a reminder of how much mystery still exists in the modern world. In a time when it sometimes feels like everything has been discovered, the ocean whispers, "Not yet. There is still more." In the next parts of this chapter, we'll look more closely at the legends and myths that shaped humanity's view of the sea, and how those ancient mysteries still echo in our modern exploration. But for now, hold on to this thought. The ocean, vast and dark and silent, is both our oldest neighbor and our greatest unknown. Asterisk, for thousands of years, the ocean was not only a body of water, it was a world of stories. Human beings have always tried to make sense of the unknown, and before satellites, submarines, or even maps, the unknown stretched endlessly across the waves. What lay beneath them? What creatures swam in the darkness? What forces stirred the storms and pulled ships into the depths? The answers our ancestors created were as varied as their cultures, but they all carried the same feeling: awe. The sea was not empty. It was alive with spirits, gods, monsters, and mysteries. Asterisk, in ancient Greece, the ocean was ruled by Poseidon, the god of the sea, earthquakes, and horses. Sailors believed that Poseidon's moods controlled the weather. A calm voyage meant he was pleased. A sudden storm meant he was angry. To this day, the word Poseidon evokes the idea of a powerful, unpredictable force that cannot be tamed. But the Greeks were not alone. In Norse mythology, the sea was home to Jormungandr, the world serpent, so large that it encircled the earth and held its own tail in its mouth. If the serpent ever let go, it was said the world would end in a great flood. For the Norse people, who lived by harsh northern waters, the ocean was both a source of life and a reminder of danger. In Polynesian cultures, the ocean was a vast, living presence. It was the pathway between islands, the source of food, and a spiritual realm. Stories told of great navigators guided by the stars of spirits that protected or punished sailors, and of journeys into the deep as a way of connecting with ancestors. Even in the Middle East, the sea carried mythical weight. In Babylonian stories, Tiamat, the goddess of salt water, represented chaos itself. Her defeat by the god Marduk was said to bring order to the universe. In this way, the ocean symbolized the primal chaos from which all things were born. Across the globe, In culture after culture, the pattern is the same. The ocean is more than water. It is mystery given form. Beyond gods and spirits, ancient sailors filled the deep with creatures. Sea monsters were a way of explaining what couldn't be understood. Sudden shipwrecks, vanishing vessels, shadows beneath the waves. The Greeks spoke of Scylla and Charybdis, two monsters that guarded a narrow strait. Scylla was a many-headed beast that snatched sailors from their ships. Charybdis was a whirlpool that swallowed entire crews whole. To sail between them meant choosing which danger you feared more, a story that later gave us the phrase between a rock and a hard place. In the Middle Ages, sailors told of the Kraken, a monstrous squid that could drag entire ships into the depths. While these stories sounded like fantasy, modern science has revealed that giant squid do exist, with tentacles stretching up to 13 meters long. Perhaps those myths weren't so far from truth after all. Another common legend was the mermaid, half-human, half-fish beings who sang to sailors and lured them off course. Some cultures saw them as protectors, others as omens of disaster. Today, scientists suggest that early sailors might have mistaken manatees or dugongs for mermaids in the distance. Yet the legend endured, because the image of a mysterious being at the border of human and ocean life was too powerful to let go. These stories were not just entertainment. They were survival tools. By telling tales of monsters, sailors taught each other to respect the sea, to prepare for danger, and to remember that the ocean always had the final say. The fear of the unknown. Why do the oceans inspire such fear? Part of the answer lies in human psychology. We are creatures of the land. Our senses are designed for light, air, and solid ground beneath our feet. The ocean is the opposite of all of that. It is dark, weightless, and alien. To step into the sea is to leave behind the familiar and enter a place where our instincts fail. This is why, even today, with scuba gear and submarines, people often feel uneasy in deep water. It is not only the thought of sharks or other predators. It is the vastness itself, the idea of being surrounded by an environment we cannot control. The fear is ancient, built into our species from countless generations of watching waves crash against the shore and wondering what lay beyond. But fear was never the whole story. The ocean also inspired dreams. Myths of lost cities like Atlantis spoke of civilizations swallowed by the waves, waiting to be rediscovered. Legends of islands that appeared and disappeared with the tides gave sailors hope of new lands. Even the monsters carried a sense of fascination, if such creatures existed. Then the world was far stranger and richer than it appeared. What is remarkable is how these ancient stories still echo in our modern age. Even with all our technology, the ocean remains linked to imagination. Movies like The Abyss, Finding Nemo, or Mona retell old themes: danger, wonder, survival, and connection with something greater than ourselves. Books and documentaries still speak of sea monsters, even if today they have scientific names, and in many ways, the myths are not outdated. They are metaphors. Poseidon is no longer a god, but the ocean is still powerful enough to shape storms and earthquakes. The Kraken may not drag down ships, but giant squid do lurk in the deep. The mermaid may not exist, but countless creatures of the deep glow with strange beauty, as if reminding us that fantasy and reality are closer than we think. The myths of the sea tell us something important. The mystery of the ocean is not just physical. It is also emotional, spiritual, and symbolic. The reason we have explored so little of the ocean is not only because it is hard, it is also because it resists being fully known. Like a story that never ends, it keeps pulling us deeper, asking us to imagine, to dream, and to respect what we cannot yet see. So, as we leave this part of our journey, remember the legends: gods who shook the waters, monsters that guarded the straits, and mermaids who sang beneath the moon. They are not only relics of the past, They are reminders of how mystery shapes the human mind. In the next section, we will move from myth into science. We'll begin to ask, what makes the ocean physically so difficult to explore? Barriers of technology, pressure, and environment stand between us and the hidden 95%. For now, hold on to the image of the ocean, not just as water, but as story. A story that humanity has been telling itself since the very beginning. As we leave behind the stories of gods, monsters, and mermaids, we step into a world that is both real and just as mysterious, the scientific exploration of the ocean. While myths gave humans a framework to imagine the sea, science provides tools to understand, measure, and sometimes challenge what we thought was impossible. Yet even today, after centuries of research, the oceans remain largely unexplored, reminding us that reality can be as wondrous as fantasy. Long before satellites and submersibles, humans were drawn to the sea with curiosity and courage. Ancient sailors in the Mediterranean, the Indian Ocean, and the Pacific navigated by stars, currents, and winds, venturing farther than anyone expected. They didn't have submarines or sonar, yet their journeys laid the foundation for modern oceanography. These explorers faced countless unknowns, unpredictable storms, sudden whirlpools, and dangerous sea creatures. Yet their observations slowly began to reveal patterns in the waves, the tides, and even the movements of marine life. By the 18th and 19th centuries, scientific expeditions became more systematic. Ships were outfitted with early tools to measure depth, water temperature, and salinity. Soundings were taken by dropping weighted ropes into the water, sometimes for miles, to map the seabed. Collecting marine specimens became a way to document biodiversity, revealing creatures so strange they seemed as unreal as the myths we discussed. Despite these advancements, scientists quickly realized that the ocean is extraordinarily difficult to explore. One reason is pressure. For every 10 meters you descend, water pressure increases by about 1 atmosphere. In the Mariana Trench, over 11 kilometers deep, the pressure exceeds 1,000 times that at sea level. Ordinary materials and human bodies cannot withstand this crushing force, which is why specialized vessels and remotely operated vehicles are required. Another challenge is darkness. Sunlight penetrates only the upper 200 meters of the ocean, known as the euphotic zone. Below this, in the aphotic zone, perpetual darkness reigns. Humans cannot see naturally in this environment. Everything must be illuminated artificially, often with powerful lights that disturb the natural behavior of marine life. Communication and navigation in this lightless world also become immensely difficult. Temperature adds another layer of complexity. Deep sea waters hover just above freezing, except near hydrothermal vents, where water superheats to hundreds of degrees Celsius. Exploration equipment must withstand extreme cold and heat simultaneously. Salinity, currents, and unpredictable underwater terrain add further obstacles. Even with modern technology, we are only scratching the surface of understanding this environment. Over the past century, humanity has made remarkable strides. Submersibles like the bathyscaphe Trieste in 1960 descended into the Mariana Trench, opening the abyss to human eyes for the first time. Remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, now map the ocean floor with extraordinary detail. Sonar and satellite altimetry help create bathymetric maps that reveal hidden underwater mountains, valleys, and plains. Yet even with all this technology, exploration is slow and costly. A single deep-sea expedition can cost millions of dollars, and equipment failures are common. Every descent into the unknown risks damage to the vessel, instruments, or even human life. The ocean is resiliently mysterious, refusing to give up its secrets easily. Science has revealed an ocean full of creatures stranger than any myth. Deep-sea fish with bioluminescent lures, jellyfish that drift silently for kilometers, and crustaceans adapted to crushing pressures, all exist in realms humans rarely see. Each new species reminds us that the unknown world beneath the waves is vast and filled with life beyond imagination. Moreover, the ocean plays a critical role in regulating life on Earth. Currents distribute heat, oceans absorb carbon dioxide, and countless organisms contribute to the planet's oxygen supply. The more we explore, the more we understand how essential this vast hidden ecosystem is, not just as a subject of curiosity, but as a lifeline for humanity itself. Even with modern science, the ocean remains a frontier as vast as space. We have mapped only a fraction of its floor. How much of its biology, chemistry, and geology remains undiscovered. Every expedition reveals surprises, volcanic vents in places thought lifeless, unknown species with extraordinary adaptations, and ecosystems thriving in complete darkness. This combination of mystery and discovery mirrors the way the ocean has always fascinated us. Like ancient myths, science inspires awe. The difference is that now we can observe, measure, and sometimes even interact with the previously invisible. Yet, for all our progress, the ocean refuses to be fully tamed. Its enormity, darkness, and pressure protect its secrets, preserving the feeling of wonder that has inspired humanity for millennia. As we finish this part of Chapter 1, let yourself drift with the idea that beneath the waves lies a world of unimaginable scale, mystery, and beauty. The myths of old and the discoveries of science both converge in this thought. The ocean is alive, profound, and far from fully understood. Its depth reminds us that even in the modern age, there are still places on Earth where the unknown dominates, where curiosity and imagination ruled in the next chapter. We will explore the technological innovations that might one day allow us to see 95% of the oceans we haven't explored. We will journey through sonar mapping, deep-sea drones, submersibles, and even speculative ideas for future exploration. For now, rest your mind in the rhythm of the waves, the silent mystery, and the promise that so much of the Earth remains a story yet to be told. As we leave the myths and early scientific discoveries behind, we begin to descend into the hidden depths of the ocean, a world largely untouched, where the rules of light, pressure, and biology create an environment unlike anything on the surface. While the myths taught humanity to respect the unknown, science is now revealing the intricacies of these submerged realms. And yet, even with advanced technology, the majority of the ocean remains a mystery, hiding secrets that may never fully be understood. To truly grasp the challenge of ocean exploration, we must understand the ocean's vertical structure. The ocean is not uniform. It is divided into several layers, each with its own characteristics. Epipelagic zone, 0 to 200 meters. The sunlight zone, where most marine life, including fish, plankton, coral reefs, thrives. Humans are familiar with this layer because it is visible from the surface. Sunlight allows photosynthesis, supporting an entire ecosystem. Mesopelagic zone, 200 to 1,000 meters, known as the twilight zone. Sunlight diminishes here. Creatures in this zone are adapted to low light, many using bioluminescence to attract prey or mates. This is a mysterious layer because visibility is limited and pressure begins to increase significantly. Bathypelagic zone, 1,000 to 4,000 meters. The midnight zone, completely dark and cold. Temperatures hover near freezing and pressure becomes extreme. Life here is strange and fascinating. Giant squid, anglerfish, and gelatinous animals adapted to darkness and crushing weight. Abyssopelagic zone, 4,000 to 6,000 meters. The abyss. Very little is known about this layer, yet it contains complex terrain, deep trenches, and unique ecosystems, often around hydrothermal vents. Adal zone, 6,000 to 11,000 meters. The deepest part of the ocean, found in trenches like the Mariana. This zone is so extreme that human exploration is rare, and machines must withstand extraordinary pressure. Each layer presents unique challenges for exploration. The deeper we go, the less we understand and the more extraordinary the life forms. Become none the deepest zones, life has evolved in astonishing ways. Bioluminescence is common, producing light through chemical reactions. Some species have elongated bodies, huge eyes, or unique adaptations to survive on minimal food. These creatures often move slowly to conserve energy in an environment where food is scarce. Predators may ambush prey with sudden bursts of speed, while scavengers feed on whatever sinks from the surface. Even bacteria thrive around hydrothermal vents, harnessing chemical energy instead of sunlight, forming the base of a complex ecosystem. These adaptations challenge our understanding of life itself, suggesting that life can exist almost anywhere. Under the right conditions, the ocean floor is not flat. It is a landscape of immense complexity. Submarine mountains, trenches, canyons, and volcanic formations create habitats for unique species. Hydrothermal vents, sometimes called black smokers, spew mineral-rich water that sustains entire communities of organisms previously unknown to science. Mapping these features is a monumental task. Sonar and submersibles provide glimpses, but large areas remain unexplored. Even minor technological glitches or weather changes can halt expeditions. The ocean's hidden terrain is both beautiful and hostile, demonstrating that exploration is not just a scientific endeavor, but an act of courage. Despite centuries of exploration, humans have only mapped a fraction of the ocean floor. Estimates suggest roughly 20% at high resolution. The remaining 80% remains a mystery, comparable to the surface of distant planets in terms of what we know. This is partly because of the sheer size and inaccessibility, and partly because of the immense cost and technical challenges. Exploration requires patience, creativity, and resilience. The ocean pushes the limits of engineering, physics, and biology. Each expedition may uncover new species, unexpected geological features, or chemical anomalies that challenge previous assumptions. And every discovery reminds us that the unknown is not an empty space, but a dynamic, living and unpredictable realm. Exploring the ocean's hidden depths is not only physically demanding, but also mentally taxing. Darkness, isolation, and immense pressure can affect perception and decision-making. Deep-sea explorers often report a mix of awe, fear, and humility when facing these alien environments. This psychological dimension adds another layer of challenge. Humans must not only survive the environment, but also maintain clarity of thought to conduct meaningful research as we conclude this first part of Chapter 2. Let your mind drift into the hidden layers of the ocean. Imagine descending through twilight and midnight zones, witnessing glowing creatures, unexplored valleys, and the unending darkness that surrounds you. The ocean is a living, breathing mystery. And while technology allows us glimpses, its depths will always inspire wonder. In Part 2, we will explore modern technologies and techniques that scientists use to push further into the deep. From autonomous drones to deep-sea submarines and sonar mapping, and discuss how these tools are helping us uncover what was once thought unknowable. As we continue our descent into the hidden depths, imagine the water around you growing colder, heavier, and more silent. Sunlight, which once filtered through the surface, has long disappeared, leaving only darkness that feels alive, as though the ocean itself is watching. Here, movement is slow and deliberate, both for the creatures and for any humans or machines daring to explore this world. Every ripple in the water, every faint shadow, becomes significant, a potential clue to life forms or geological structures. Unseen, the pressure, immense and relentless, presses against every surface, a reminder of the ocean's raw and unyielding power. To survive here, vessels must be engineered with extraordinary precision. And explorers must confront not only physical challenges, but a sense of isolation few can imagine. As we glide further, the creatures that inhabit these depths reveal themselves in flashes of bioluminescence. Small dots of light flicker, some pulsing rhythmically, others sparking with sudden intensity. These living lights serve as signals, lures, or warnings. A language of survival written in glowing script across the black canvas of the sea. Strange shapes emerge, elongated bodies undulating slowly, eyes adapted to detect the faintest trace of movement, mouths filled with unexpected arrays of teeth designed for efficiency rather than beauty. Each encounter challenges assumptions about biology, adaptation, and the sheer creativity of evolution in extreme conditions. The deeper we go, the stranger the forms become, until the ocean seems almost extraterrestrial in its diversity and ingenuity. The terrain beneath us is equally remarkable. Towering underwater mountains rise like ancient citadels, their peaks shrouded in darkness. Valleys stretch into obscurity, holding sediments and structures that may be millions of years old. Volcanic formations occasionally punctuate the seafloor, releasing heat and minerals that create isolated ecosystems thriving without sunlight. Here, life clings to chemical energy, deriving sustenance from substances humans cannot directly perceive, forming complex webs that hint at the resilience of life even in seemingly impossible environments. Every ridge, every trench holds secrets that could rewrite what we know about marine biology, geology, and the limits of survival. Exploration of this world is slow, deliberate, and often frustrating. Submersibles inch along, their lights cutting through the darkness, revealing creatures that vanish as quickly as they appear. Sensors record data that may take months or years to analyze fully, while maps of the seafloor slowly grow more detailed, piece by piece, revealing the astonishing complexity of the ocean's architecture. Even with these tools, vast areas remain untouched. A reminder that for all our technology, the ocean is still an ancient, almost alien landscape that resists full comprehension. The ocean's depths evoke a profound psychological response. Silence dominates, punctuated only by the faint hum of machinery or the distant rumble of tectonic activity. The absence of light, the immense space around, and the slow, graceful movements of creatures create a sense of humility, awe, and, at times, unease. It is a realm that inspires wonder and fear in equal measure, where the familiar laws of surface life no longer apply, and where every discovery deepens the sense of mystery rather than reducing it as we drift through this unseen world. It becomes clear that the hidden depths are more than just a physical frontier. They are a gateway to understanding resilience, adaptation, and the limits of human curiosity. Every organism, every rock formation, every plume of chemical-rich water tells a story of survival and complexity. This is a world where life finds a way against unimaginable odds, and where the oceans, vast, unexplored stretches hold secrets that challenge our imagination and scientific understanding alike. As this part of our journey concludes, imagine the quiet grandeur of the deep, the flickering bioluminescent signals of unknown creatures, and the endless expanse of darkness punctuated by mountains and valleys sculpted over eons. Let your mind linger on the knowledge that beneath the waves, a living, breathing universe exists, largely untouched and waiting to reveal its wonders to those patient and daring enough to explore. In the next part, we will continue our descent, focusing on the incredible tools and technologies that allow humans to study this extreme environment in unprecedented detail, and the discoveries that have reshaped our understanding of the ocean and its role in the planet's ecosystem. As we press further into the ocean's hidden realms, the weight of the water above grows heavier, and the silence becomes almost tangible. It is a stillness that feels alive, as though the very sea is breathing around us. Every movement of the submersible or autonomous drone creates subtle ripples, and each flicker of light illuminates fleeting glimpses of life forms perfectly adapted to the pressure, cold, and darkness. In this world, time seems different. Minutes stretch, the mind slows, and awareness shifts to the present moment. Observing the quiet rhythm of the deep. Beneath the surface, the terrain is astonishingly varied. Steep cliffs rise from the abyss, covered in soft corals and bacterial mats that glow faintly. Trenches plunge into seemingly endless darkness. And hydrothermal vents release clouds of mineral-rich water, sustaining unique ecosystems. These vents are oases of life in a vast, otherwise barren environment. Here, entire communities of tube worms, clams, and shrimp thrive without sunlight, relying entirely on chemosynthesis. The presence of such ecosystems demonstrates the incredible adaptability of life, showing that even in extreme conditions, energy flows, life evolves, and ecosystems flourish. Creatures of the deep are both mesmerizing and alien. Jellyfish drift like translucent ghosts, their delicate tentacles trailing silently. Deep-sea fish, often with enormous jaws or luminescent lures, move with slow precision, conserving energy in an environment where food is scarce. Some species display bioluminescent patterns that communicate with others of their kind, while others flash sudden bursts of light to confuse predators or attract prey. Every encounter challenges our perception of what life can look like, how it can survive, and how it can interact with its environment in ways that seem almost magical. The pressures of these depths are beyond what humans can naturally withstand. Every descent is a careful balance of engineering, technology, and courage. Submersibles are reinforced to endure thousands of pounds of pressure per square inch. Their hulls designed to resist crushing forces that would obliterate ordinary vessels. Cameras, lights, and sensors extend our senses, allowing us to record data about temperature, salinity, chemical composition, and the presence of life. Despite these technological advances, exploration is painstakingly slow. Every mission is planned with precision, every maneuver deliberate, because a single miscalculation could endanger equipment, data, or life. Exploration also reveals the unexpected. Species previously unknown to science emerge from crevices or drift lazily past observation windows. Geological formations defy simple description: mountains, valleys, and ridges sculpted over millions of years, some taller than the tallest peaks on land. These structures not only provide habitats for life, but also record the history of Earth's geological and climatic changes. Every rock, every mineral, every plume of chemical-laden water tells a story, a narrative of creation, adaptation, and survival. The deep sea is also a reflection of human curiosity and ingenuity. Each expedition expands the limits of what is known, pushing both technology and imagination. While we have mapped only a fraction of these depths, even limited glimpses inspire profound questions. How did these organisms evolve? What secrets are hidden in unmapped trenches? Could life exist in similar, extreme conditions elsewhere in the universe? The ocean becomes a mirror, reflecting our desire to understand the unknown and our determination to reach beyond our limitations. As we drift silently through this realm, it is impossible not to feel a sense of humility. The ocean's hidden depths are vast, uncharted, and indifferent to human presence. They challenge our understanding of life, energy, and the interconnectedness of ecosystems. Yet, they also offer wonder, inspiration, and a quiet reminder that some of the most extraordinary worlds are right here on our own planet, waiting patiently to be discovered. Allow your mind to linger on these thoughts, letting the darkness and quiet of the deep sea settle around you. Imagine the flickering lights of unseen creatures, the massive mountains and deep valleys hidden beneath the waves, and the slow, graceful movements of life in complete darkness. The ocean is alive, mysterious, and endlessly captivating, a universe. Beneath the universe we know, inviting exploration, contemplation, and awe. As we leave the hidden wonders of the deep behind, our attention turns to the incredible technologies that allow humans to explore these otherwise inaccessible realms. Without these tools, much of what we know about the ocean's depths would remain an impossible dream. Imagine the silent, crushing darkness, the extreme pressure. These are not conditions that humans can endure without protection. Every deep-sea expedition relies on a delicate balance of engineering, imagination, and endurance, merging the ingenuity of human minds with the relentless mysteries of the ocean. The first tool that comes to mind is the manned submersible, a marvel of engineering. These small, pressurized vessels allow scientists to descend into the depths while remaining safely enclosed. Their hulls are crafted from thick steel or titanium, designed to resist the thousands of pounds of pressure per square inch that bear down from above. Inside, scientists can observe the environment directly, record data, and take samples. Every light, every camera, every instrument is carefully calibrated to survive the darkness, the cold, and the crushing weight of the ocean. Manned submersibles represent a combination of human courage and technological precision, giving researchers a glimpse into a world that few have ever seen firsthand. Alongside these, autonomous underwater vehicles (AUVs) operate without humans aboard, diving into the depths on pre-programmed missions. These machines navigate through complete darkness, mapping the seafloor with sonar, recording environmental data, and even capturing footage of previously unknown species. AUVs can explore areas that would be too dangerous or remote for manned vessels, extending our reach into trenches, ridges, and hydrothermal vent fields. Their ability to function autonomously makes them invaluable, and their data often leads to discoveries that inspire entire new research projects. Another critical technology is remotely operated vehicles, ROVs, tethered to a ship on the surface. These vehicles combine the reach of machinery with the oversight of human operators. Scientists control them in real time, maneuvering through narrow crevices, collecting delicate specimens, and observing life in its natural habitat. ROVs often have robotic arms capable of intricate movements, allowing precise sampling of sediments, minerals, or living organisms. This combination of human judgment and mechanical strength makes ROVs essential for deep-sea research, bridging the gap between human curiosity and the ocean's unforgiving environment. The sensors and imaging equipment on these vehicles are equally extraordinary. High-definition cameras, sonar arrays, chemical sensors, and pressure gauges allow researchers to collect data in a world where traditional measurement methods would fail. Light must be carefully controlled to avoid disturbing creatures adapted to darkness, and sonar must be used strategically to map landscapes without harming the ecosystem. Even minor technological errors can compromise years of data or place equipment at risk, highlighting the delicate balance required for successful exploration. Innovations in underwater communication are also critical. Radio waves do not travel far underwater, so acoustic signals, lasers, and fiber optic tethers are used to transmit information. This allows teams on the surface to monitor conditions, receive images, and guide missions in real time. The development of these communication systems has transformed deep-sea exploration, making it more precise, safe, and efficient. Even with all this technology, challenges remain. Submersibles and AUVs are expensive to build and operate, and harsh weather, ocean currents, and technical malfunctions can halt a mission. The extreme environment pushes both machinery and humans to their limits. Yet, despite these obstacles, each mission brings new insights, uncovering species, geological formations, and chemical processes that expand our understanding of the planet's oceans. As we drift through this technological landscape, imagine the quiet hum of machinery in the crushing darkness, the slow rotation of lights illuminating alien shapes, and the delicate movements of robotic arms reaching into unknown worlds. Each device is an extension of human curiosity, a tool that allows us to interact with an environment that would otherwise remain completely inaccessible. Through these technologies, we are not merely observing. We are participating in the story of discovery, pushing the boundaries of knowledge and witnessing life in landscapes that few have ever imagined. As we move further into the story of deep-sea technology, it is impossible not to marvel at the historic breakthroughs that have made exploration possible. In the early days, human curiosity was limited by the fragility of vessels and the dangers of extreme pressure. Even diving a few hundred meters required immense courage and ingenuity. Early submersibles were small, often experimental, and only capable of brief descents. Yet, each attempt laid the foundation for the sophisticated machines we rely on today. Every success expanded our understanding of the deep, while every failure reminded us of the ocean's indifference and power. Modern manned submersibles such as the Alvin and the Deep Sea Challenger represent the pinnacle of this evolution. These vessels have reached depths previously thought unreachable, allowing scientists to observe ecosystems that exist in perpetual darkness. Alvin, for example, famously explored hydrothermal vents in the Pacific, revealing entire communities of organisms thriving without sunlight. These discoveries were revolutionary, showing that life can exist in environments powered not by the sun, but by the chemical energy of the Earth itself. The Deep Sea Challenger, piloted by explorer James Cameron, descended to the Mariana Trench, capturing unprecedented footage and data from the ocean's deepest point. Such achievements combine technical precision, courage, and the relentless human desire to understand the unknown. Autonomous underwater vehicles, IUVs, have also transformed exploration. Equipped with advanced sonar and mapping systems, they can scan vast areas of the seafloor, creating detailed maps that reveal geological formations, trenches, and ridges. AUVs are often deployed in places too dangerous for human-occupied submersibles, and their autonomous operation allows them to explore continuously for days or weeks. The data collected by these machines has reshaped oceanography, revealing previously unknown underwater mountain ranges, deep trenches, and sediment patterns that inform our understanding of Earth's geological history. Remotely operated vehicles, ROVs, extend human reach even further. Controlled from ships on the surface, they can maneuver with incredible precision, capturing high-resolution images and collecting delicate samples. Some ROVs are equipped with robotic arms capable of intricate movements, allowing scientists to handle fragile organisms or take sediment samples without disturbing the surrounding environment. These machines bridge the gap between human curiosity and the ocean's unforgiving conditions, providing a window into the behaviors and adaptations of deep-sea life. Sensors and imaging technology continue to advance at a rapid pace. Definition, cameras, multispectral imaging, chemical sensors, and pressure gauges allow researchers to collect data with unparalleled accuracy. Bioluminescent signals, water chemistry, and the faintest movements of organisms can now be observed in real time. Sonar mapping reveals the contours of the seafloor with astonishing detail, while temperature and chemical analysis help scientists understand the dynamics of deep-sea currents and ecosystems. Each advancement brings us closer to comprehending a world that is still largely unknown. Communication remains a challenge in these extreme depths. Radio waves are quickly absorbed by water, so explorers rely on acoustic signals, fiber optic cables, and laser-based communication systems. These technologies allow surface teams to monitor submersibles, guide missions, and receive real-time data. Such systems are crucial for safety and for ensuring that no opportunity for discovery is lost. Despite these remarkable tools, the ocean remains largely unexplored. Only a fraction of its vast expanse has been mapped or studied, and each new expedition reveals surprises. Giant squid, previously thought mythical, have been filmed in their natural habitat. Hydrothermal vent communities, thriving on chemosynthesis, challenge our assumptions about the necessities of life. Entire underwater mountain ranges remain uncharted, their peaks and valleys holding the potential for countless discoveries. As we move into the final part of this chapter, our focus turns to the extraordinary discoveries made possible by deep-sea technologies. Discoveries that were unimaginable just a few decades ago. Every submersible dive, every autonomous mission, and every remotely operated exploration has expanded our understanding of the deep ocean, revealing life forms, geological structures, and ecosystems that challenge our perception of Earth itself. Among the most striking finds are the hydrothermal vent communities, which exist in complete darkness, hundreds of meters below the surface. These vents emit mineral-rich fluids heated by the Earth's magma, creating unique chemical environments. In these isolated pockets, life flourishes in ways that were once thought impossible. Tube worms, clams, and shrimp rely on chemosynthesis. Instead of photosynthesis, deriving energy from chemicals in the water rather than sunlight. Observing these communities through manned submersibles and ROVs has not only expanded our understanding of biological adaptability, but also sparked speculation about the potential for life in similar extreme environments elsewhere in the universe. Then, there are the giant squids and other elusive creatures, which were previously considered the stuff of legend. Using deep-sea cameras and sonar tracking, scientists have managed to capture footage of these massive animals, providing insights into their behavior, feeding patterns, and interactions with their environment. The slow, deliberate movements of these creatures, perfectly adapted to high-pressure darkness, are mesmerizing and almost hypnotic, drawing attention to the intricacy and mystery of life in the abyss beyond life. Deep-sea exploration has revealed geological wonders. Vast underwater mountain ranges rise from the ocean floor, some larger than the tallest mountains on land. Deep trenches plunge to depths that remain largely unexplored, holding clues about Earth's geological past. Submarine volcanoes, hydrothermal vents, and unique mineral formations have been documented, illustrating the dynamic processes shaping the planet from beneath the waves. Sonar mapping and high-resolution imaging allow scientists to study these formations in detail, providing not only scientific insight, but also awe-inspiring imagery that captivates the imagination. Living fossils, species that have remained unchanged for millions of years, offer a glimpse into evolutionary history. Certain fish, invertebrates, and microbial life forms discovered at extreme depths exhibit traits that connect them to ancient ancestors, helping scientists understand the trajectory of life on Earth. These discoveries highlight the ocean as a living museum, preserving relics of a past that is otherwise inaccessible on land. Technological innovations continue to push the boundaries. Modern submersibles are now equipped with advanced robotic arms, high-definition imaging systems, and environmental sensors that can detect even the slightest chemical or temperature variations. Autonomous vehicles can navigate complex terrain, mapping thousands of square kilometers of seabed without human intervention. Each new mission builds upon the last, slowly illuminating a world that was once completely hidden. But even with these advances, the ocean remains largely unexplored. It is estimated that over 95% of the deep sea is still unmapped. Every expedition, therefore, carries the possibility of a groundbreaking discovery on unknown species, an unusual ecosystem, or a geological formation unlike anything seen before. This uncertainty fuels both scientific curiosity and human imagination, inspiring dreams of what lies beneath the waves and encouraging continued exploration despite the challenges. The challenges of deep-sea research are immense. Pressure, temperature, darkness, and isolation test both technology and human patience. Each dive must be meticulously planned, and even then, unexpected currents, equipment failures, or harsh environmental conditions can disrupt a mission. Yet, these challenges make each successful discovery all the more remarkable, a testament to human determination and ingenuity. As we conclude this part, allow your mind to drift among the silent depths, imagining robotic arms gently moving through fragile ecosystems, autonomous drones mapping mountains and trenches, and the ethereal glow of bioluminescent life. Visualize the unknown landscapes, the unseen creatures, and the incredible forces that shape this hidden world. Consider the enormous effort, curiosity, and courage that have allowed us to witness even a fraction of it. In the next chapter, we will explore the mysteries of oceanic life and adaptation, delving deeply into the astonishing ways organisms survive in extreme conditions, their evolutionary stories, and the lessons they hold about resilience, innovation, and survival. Asterisk. As we turn our focus to the incredible variety of life within the ocean, it becomes clear that adaptation is the key to survival in these extreme, mysterious environments. The deep sea is not merely a dark and empty abyss. It is a dynamic ecosystem, filled with creatures that have evolved remarkable strategies to thrive where sunlight cannot penetrate, where temperatures plummet, and where pressure could crush an unprotected human in an instant. One of the most striking adaptations is bioluminescence, the ability of certain organisms to produce their own light. Tiny plankton, jellyfish, and even fish use this ability for multiple purposes: to attract prey, to camouflage themselves, to communicate, or to deter predators. Imagine the slow, flickering glow of a squid against the darkness, each pulse of light a silent signal, a survival tactic honed over millions of years. In the absence of sunlight, these glowing beacons serve as vital lifelines, helping creatures navigate, find food, and avoid danger. The diversity of bioluminescent patterns is astonishing, with some organisms producing continuous glows, others flashing in rapid sequences, and some even emitting light in unexpected colors or wavelengths that are visible only to certain species. The extreme pressure of the deep sea has also driven unique physiological adaptations. Fish and invertebrates have evolved flexible, gelatinous bodies that can withstand thousands of pounds of pressure per square inch. Their bones may be reduced, muscles adapted, and organs specially reinforced. These creatures often have slow metabolisms, conserving energy in a world where food is scarce. Even their enzymes and cellular structures are designed to function efficiently under conditions that would cause ordinary life to collapse. Feeding strategies in the deep are equally extraordinary. Some predators use extensible jaws and stomachs, allowing them to consume prey much larger than themselves. Others rely on filter feeding, absorbing microscopic organisms that drift in the ocean currents. In areas near hydrothermal vents, entire ecosystems depend not on sunlight but on chemosynthesis, a process where bacteria convert chemicals like hydrogen sulfide into energy. Tube worms and clams host these bacteria internally, creating a symbiotic relationship that supports entire communities in the harshest of taxing environments. Reproduction in the deep sea has also evolved in unusual ways. Many species are hermaphroditic, capable of producing both eggs and sperm, ensuring that encounters with mates are not wasted. Some fish exhibit extreme sexual dimorphism, with males evolving as parasitic or specialized creatures whose sole purpose is to find and fertilize a female in the darkness, where encounters are rare. Such adaptations maximize reproductive success and maintain population stability. Camouflage is another essential adaptation. Many deep-sea creatures are transparent or possess reflective scales, blending seamlessly with their surroundings. Others have dark, matte bodies to avoid detection in the absence of light. Some use counter-illumination, producing light on their undersides to match the faint light from above, rendering them nearly invisible to predators looking up from below. These evolutionary innovations illustrate the ingenuity of life under extreme conditions. Predation and defense strategies are equally diverse. Some creatures have developed spines, toxins, or bioluminescent decoys to escape threats. Others exhibit unusual behaviors, such as glowing to mislead predators or mimicking other species. In the deep, survival requires both adaptation and cunning. And evolution has produced a plethora of strategies to navigate the balance between hunter and prey. Temperature also plays a critical role in adaptation. Deep-sea organisms often inhabit environments near freezing. Yet some thrive near hydrothermal vents with temperatures exceeding 400 degrees Celsius. Heat-resistant enzymes, specialized cellular membranes, and thermally adaptive proteins allow these creatures to survive extremes that would destroy ordinary life. The ability to flourish in such disparate conditions speaks to the incredible resilience and plasticity of deep-sea life. Social behavior is another area of fascination. Some species, like certain fish and squid, display schooling behavior, coordinating movements to confuse predators or hunt collectively. Others live solitary lives, relying on stealth and patience. Communication in the deep often involves subtle cues like flashes, chemical signals, or vibrations in the water. Every interaction is a careful negotiation, a dance of survival performed in darkness, under immense pressure, and in a world entirely alien to human senses. As Part 1 concludes, imagine drifting silently above these extraordinary ecosystems, where glowing creatures float like stars in a midnight sky, where each organism is a marvel of evolutionary engineering, and where life persists against extreme odds. Let your mind wander through the glowing, gelatinous forests, past predatory fish with expandable jaws, and over communities of tube worms thriving on chemicals from the Earth's core. Consider the sheer resilience, ingenuity, and beauty of life in a world humans rarely see, and allow your thoughts to settle into the rhythm of these silent, shadowed waters. As we move deeper into the study of oceanic life, it becomes increasingly clear that adaptation is not merely about survival. It is a demonstration of nature's creativity, resilience, and ingenuity. The deeper we go, the more alien the environment becomes, and the more remarkable the organisms that inhabit it appear. Every adaptation tells a story of millions of years of evolution, shaping life to persist in a world of darkness, crushing pressure, and extreme scarcity. Consider the phenomenon of gigantism in deep-sea species, where certain creatures grow to sizes far larger than their shallow water relatives. Giant squids, colossal isopods, and even certain deep-sea jellyfish display this trend. Scientists theorize that slower metabolisms, colder temperatures, and fewer predators in the depths contribute to these remarkable sizes. For example, giant squids, elusive and rarely observed, can reach lengths exceeding 13 meters. Their enormous eyes, some of the largest in the animal kingdom, are perfectly adapted to detect faint glimmers of light from bioluminescent prey, illustrating an evolutionary solution to the challenges of hunting in perpetual darkness. Equally fascinating is the adaptation to nutrient scarcity. In the deep ocean, food is rare, and creatures have developed strategies to make the most of every meal. Some fish can go months without eating, surviving on stored energy, while others employ sit-on-wait strategies, remaining motionless for long periods to conserve energy until prey comes near. The anglerfish is perhaps the most famous example, using a glowing lure to attract unwitting victims. This kind of patience, precision, and efficiency in predation highlights how life can thrive even in resource-poor environments. Symbiosis is another extraordinary adaptation seen in deep-sea ecosystems. Many species form mutually beneficial relationships that allow them to survive where they could not alone. Tube worms, near hydrothermal vents, for example, rely on chemosynthetic bacteria housed within their bodies to convert toxic chemicals into energy. Without these bacteria, the worms would perish. Yet the bacteria, in turn, are nourished and protected by their host. This intricate cooperation illustrates the interconnectedness of life in extreme conditions and the delicate balance that sustains these unique ecosystems. Reproductive adaptations in the deep ocean are equally compelling. In a world where encounters with mates are rare, certain species have evolved strategies to maximize reproductive success. Some fish, like deep-sea anglerfish, display extreme sexual dimorphism, with tiny males attaching to much larger females for life, serving only to fertilize eggs. Other species are hermaphroditic, capable of producing both eggs and sperm to ensure that no encounter is wasted. These adaptations underscore the creative solutions life finds to maintain populations in seemingly inhospitable environments. Another fascinating aspect of deep-sea adaptation is the use of pressure-resistant physiology. At extreme depths, pressure can exceed 1,000 times the surface level. Yet organisms like deep-sea fish, crustaceans, and invertebrates exhibit remarkable resilience. Their cellular structures, enzymes, and membranes are all specially adapted to function under intense pressure, ensuring that biochemical processes continue without interruption. Flexible, soft bodies, reduced skeletal structures, and specialized fluids within cells contribute to their ability to survive where humans cannot. Sensory adaptation also plays a crucial role. In near-total darkness, sight is often replaced by other senses. Many species rely on lateral lines to detect vibrations in the water, while others sense electric fields generated by nearby organisms. Some have evolved highly sensitive eyes, capable of detecting bioluminescent glows or subtle variations in light intensity. Others depend on chemical cues or even sonar-like echolocation to navigate and locate food. These adaptations provide alternative ways to perceive and interact with the environment when traditional senses fail. Predation and defense strategies continue to amaze. Deep-sea organisms employ deception, mimicry, and extreme specialization to survive. Some fish use transparency to become nearly invisible, while others reflect ambient light to blend into their surroundings. Bioluminescent flashes can confuse predators or lure prey, and venomous spines provide protection from attacks. These evolutionary innovations create a complex and dynamic food web, where each organism is both hunter and potential prey. Finally, adaptation extends to behavior and social organization. Some species exhibit schooling behavior to improve hunting efficiency or reduce the likelihood of predation. Others are solitary, relying on stealth and patience to survive. Communication in the deep is subtle and sophisticated, often involving light signals, chemical cues, or vibrations in the water. Every interaction, whether cooperative or predatory, reflects the delicate balance of life in the abyss. As Part 2 concludes, imagine drifting silently among these extraordinary ecosystems, where every creature is a marvel of evolutionary engineering, each adapted in ways both subtle and extreme to survive. Visualize the glowing forests of bioluminescent organisms, the slow motion of gelatinous giants, and the intricate symbioses that sustain life in this alien world. Let your mind settle into the rhythm of these hidden depths, where adaptation is not only survival, but a testament to the resilience, creativity, and beauty of life itself. As we enter the final part of this chapter, our attention turns to the most extraordinary and extreme adaptations that have allowed life to flourish in the deepest, darkest regions of the ocean. These adaptations are not merely fascinating. Challenge our understanding of biology, evolution, and the resilience of life itself. One of the most remarkable adaptations is extreme bioluminescence. While many creatures use light for simple camouflage or communication, Some deep-sea organisms have evolved highly specialized and intricate light-producing abilities. Consider the lanternfish, which generates patterns of light along its body to confuse predators or signal others of its species. Certain deep-sea squids have developed bioluminescent displays so precise that they can mimic the flickering of distant prey or produce bursts of light to stun attackers. Imagine these silent, glowing flashes in the inky darkness, a mesmerizing dance of survival and strategy that seems almost deliberate, almost intelligent. In addition to light, pressure-resistant physiology reaches new extremes. At the greatest depths, some creatures live under pressures exceeding 1,000 times that at the surface. These organisms exhibit incredibly flexible, almost gelatinous bodies, minimizing internal damage from crushing forces. Their cellular structures are reinforced with unique proteins, and enzymes are engineered to function efficiently under intense compression. This allows entire communities of organisms to survive in regions where ordinary life would instantly collapse, highlighting the extraordinary adaptability of living systems. Food scarcity drives incredible feeding strategies. Deep-sea predators often display extreme opportunism. The gulper eel, for instance, has an expandable jaw capable of swallowing prey far larger than itself. Other organisms, like deep-sea anglerfish, employ glowing lures to attract prey into striking range. Some species survive primarily on marine snow tiny particles of organic slushy melm. Organic slushy / only ruby kiss. Only ruby kiss has the luxurious texture that glides on smoothly. La lies. Unlasting claws, long later / long-lasting color. Striking lies. Triking rains. Some species survive, like recive. De lies, my reside. Beway, my a salive. De bissa bei, it bows exped, but it's a resocide, but it's exad. By minutes odd sil I said, I resisle sakaka se you be kiss it to kai, it's a sickweep kide my less, it's a sext to pita sus, it's a guidance, material drifting from the surface, consuming every bit of available energy to survive. These strategies reflect the intense pressures of a nutrient-poor environment and the ingenuity of evolution in overcoming scarcity. Reproductive adaptations continue to fascinate. In regions where encounters with mates are rare, extreme strategies have evolved. Some fish are hermaphroditic, ensuring that any encounter can result in reproduction. Others, like certain anglerfish species, exhibit permanent parasitic males. Tiny creatures that attach to a larger female and exist solely to fertilize her eggs. This method guarantees reproductive success in an environment where chance encounters are exceedingly rare. Illustrating nature's creative solutions to the challenge of life in the deep, camouflage and deception reach heights that seem almost alien. Some species use transparency to vanish entirely against the faint ambient light. Others employ counterillumination, producing light on their undersides to match faint rays from above, making them nearly invisible to predators below. Bioluminescent decoys or sudden flashes can startle attackers or distract prey, adding layers of complexity to survival. Every adaptation reflects millions of years of evolution, fine-tuned to maintain the delicate balance between predator and prey. Temperature extremes also drive astonishing adaptation. Some creatures live near hydrothermal vents where temperatures can soar to several hundred degrees Celsius while just meters away. The water can hover near freezing. Proteins and cellular membranes are specially adapted to maintain functionality across these ranges. Some microbial life thrives solely on the chemical energy from vents, independent of sunlight, revealing entirely new paradigms of life's potential. Social behavior and communication are subtle but crucial. Many deep-sea species rely on coordinated movement, schooling, or collective hunting, while others remain solitary, using stealth and patience to survive. Communication is often visual, using bioluminescent flashes or chemical, releasing pheromones into the water. Even in total darkness, life finds a way to interact, coordinate, and survive. Finally, consider the living fossils of the deep. Certain fish, invertebrates, and microbial species have remained virtually unchanged for millions of years. These organisms provide a window into evolutionary history, revealing traits and strategies that existed long before humans walked the earth. They are a testament to the power of adaptation, to survival across epochs, and to the mysteries that the deep ocean still holds. As we conclude Part 3, allow your imagination to drift across the abyssal plains. Through glowing forests of bioluminescent life, past colossal predators with adaptable jaws, and among creatures that defy conventional understanding of biology. Reflect on the intricate balance, the extreme adaptations, and the astonishing creativity of evolution that has allowed life to thrive in conditions that seem impossible. In the next chapter, we will explore the hidden ecosystems of underwater caves, trenches, and extreme habitats, unveiling the most secluded and mysterious pockets of life on our planet and the technologies that allow humans to glimpse these alien worlds. Beneath the surface of the ocean lie environments that are as alien as any extraterrestrial landscape. These hidden ecosystems, underwater caves, trenches, hydrothermal vents, and cold seeps offer habitats where life has evolved in isolation, developing adaptations that are extraordinary and often completely unknown to science. The physical conditions in these areas are extreme, crushing pressures, near-freezing temperatures, total darkness, and chemical compositions that would be toxic to surface life. Yet within these secluded spaces, life flourishes in remarkable ways. Consider the deep-sea trenches, the lowest points on the planet, plunging more than 10,000 meters below sea level. These environments are almost completely cut off from the sunlight that fuels photosynthesis, meaning that energy for life must come from alternative sources. Here, chemosynthetic bacteria serve as primary producers, converting chemicals like hydrogen sulfide or methane into energy. These bacteria form the foundation of the food web, supporting communities of tubeworms, clams, crustaceans, and fish, all uniquely adapted to survive on energy derived from the Earth itself rather than the sun. Hydrothermal vents, often referred to as the black smokers of the deep, release scalding water rich in minerals and chemicals. Around these vents, entire ecosystems thrive where, just meters away, temperatures plummet. Tubeworms, giant clams, and certain crustaceans host chemosynthetic bacteria within their tissues, creating symbiotic relationships essential for survival. The contrast between the extreme heat and the surrounding cold is stark. Yet life has found equilibrium, demonstrating incredible resilience and ingenuity. Underwater caves present a different set of challenges. Many of these caves are labyrinthine, with narrow passages and complete darkness. Species that inhabit them, like blind fish, shrimp, and crustaceans, have evolved highly sensitive tactile and chemical senses to navigate and find food. Eyes are often reduced or completely absent, replaced by elongated antennae, lateral lines, or other sensory organs that detect vibrations, chemical changes, and subtle water movements. The isolation of these caves also fosters endemism, with species found nowhere else on Earth, making each cave a unique repository of evolutionary experimentation. Cold seeps are another fascinating ecosystem, where methane or hydrogen sulfide leaks slowly from the seafloor. Here, life forms rely on chemosynthetic bacteria, similar to hydrothermal vent communities. But the environmental conditions are more stable and less extreme. Mussels, clams, and certain types of worms thrive in these areas, often forming dense colonies. The energy derived from chemical reactions provides a consistent source of sustenance, allowing life to persist in a way that challenges the assumption that sunlight is the primary driver of ecosystems. The adaptations required for survival in these hidden ecosystems are remarkable. Many species possess slow metabolisms to conserve energy, allowing them to survive for long periods with limited food. Flexible and pressure-resistant bodies are common, enabling organisms to withstand intense pressure. Sensory adaptations are crucial. Chemosensation, mechanoreception, and electroreception replace vision in dark environments. Predation and defense strategies are often unique, with some species producing toxins or bioluminescent displays to deter threats. Symbiotic relationships dominate these isolated habitats. In hydrothermal vent communities, the success of tube worms, clams, and shrimp depends entirely on their microbial partners. In caves, bacterial films often serve as the only available food source, and animals have evolved to scrape, graze, or filter these films efficiently. These interdependencies highlight a broader lesson. Life adapts not only individually, but collectively, creating intricate webs of cooperation that sustain entire ecosystems. The study of these hidden ecosystems also sheds light on the limits of human exploration. Many areas remain unexplored due to the technological challenges posed by extreme pressure, darkness, and remote locations. Submersibles, remotely operated vehicles, ROVs, and autonomous underwater drones have allowed scientists to peek into these alien worlds, revealing life forms and behaviors that challenge our understanding of biology. Even now, it is estimated that more than 95% of the deep ocean remains unexplored, leaving an immense frontier of potential discoveries. Beyond biology, these ecosystems also offer clues about the origins of life on Earth and the potential for life elsewhere. Chemosynthetic communities resemble conditions that may have existed on early Earth, where sunlight was scarce and chemical energy drove life. Similarly, studying organisms that thrive in extreme environments informs astrobiology, helping scientists hypothesize about life on icy moons, deep oceans of other planets, or exoplanets with subsurface oceans. Each adaptation observed in these hidden ecosystems broadens our understanding of what life is capable of, stretching the imagination toward the possibilities beyond our own world in the depths. Every environment is a microcosm of extremes, a laboratory of survival strategies. The isolation, darkness, pressure, and scarcity drive innovation in evolutionary biology, producing life forms that appear almost otherworldly. From blind, sensitive cave fish to bioluminescent predators in abyssal trenches, the ingenuity of life demonstrates resilience, cooperation, and adaptation on a scale that challenges our everyday perceptions of the ocean as merely vast water. As Part 1 concludes, picture yourself drifting silently over these hidden realms, past ghostly crustaceans, glowing microbial mats, and heat-tolerant tube worms, marveling at the delicate balance, the extreme adaptations, and the intricate webs that sustain life. Where humans rarely venture, allow the mind to absorb the strangeness, complexity, and beauty of these secluded habitats as you continue to explore the mysteries of the deep. As we journey deeper into these hidden oceanic ecosystems, it becomes clear that life has found ways to persist in even the most hostile environments. One of the most astonishing aspects of these realms is the complex interplay between geological features and biological communities. Deep-sea trenches, hydrothermal vents, cold seeps, and isolated underwater caves are not just empty voids. They are intricate landscapes, each with their own physical structure, chemical composition, and resident organisms. These unique conditions shape life in ways that are both subtle and dramatic, resulting in forms and behaviors found nowhere else on Earth. Take, for instance, the abyssal plains, vast expanses of nearly flat seabed that stretch for thousands of kilometers. At first glance, they may appear barren, yet these plains host a surprising diversity of life. Many species are scavengers, feeding on marine snow the continuous drizzle of organic material falling from the upper layers of the ocean. Others, such as deep-sea octopuses and hagfish, exhibit highly specialized hunting techniques using chemical cues and sensitive tentacles to locate prey in total darkness. The adaptations required to survive on such a resource-limited landscape are extreme, often resulting in slow growth, low reproductive rates, and extraordinary longevity. Hydrothermal vent communities continue to captivate scientists because of their self-sustaining energy cycles. Unlike most ecosystems on Earth, which rely on sunlight for photosynthesis, vent ecosystems are based entirely on chemosynthesis. Bacteria convert chemicals like hydrogen sulfide into energy, creating a foundation for the entire food web. Tube, worms, clams, and even certain shrimp species host these bacteria in symbiotic relationships, drawing their nourishment directly from their microbial partners. These relationships demonstrate an astonishing level of biological interdependence and highlight the adaptability of life in extreme conditions beyond vents and plains. Submarine canyons and caves are filled with organisms that display incredible sensory adaptations. Blind fish, crustaceans, and amphipods navigate complex networks of tunnels using enhanced tactile senses, lateral lines, or even electroreception. Many of these species exhibit endemism, meaning they are found nowhere else on the planet. The isolation of these habitats encourages evolutionary experimentation, producing forms and behaviors that might seem almost alien. Some organisms have evolved flattened bodies to squeeze through narrow crevices, while others use long antennae to sense prey or avoid predators in near-total darkness. Cold seeps, in particular, highlight the diversity of chemical energy utilization. In the deep ocean, unlike hydrothermal vents, which can be transient and volatile, cold seeps release chemicals slowly and steadily. This stability allows organisms to establish long-term colonies, relying on chemosynthetic bacteria for sustenance. Mussels, clams, and certain polychaete worms thrive here, forming dense aggregations that support predators and scavengers. These ecosystems challenge our conventional understanding of food chains, emphasizing chemical energy over sunlight and revealing alternative pathways for sustaining complex life. Predation in these hidden ecosystems is equally fascinating. Many species have evolved ambush strategies using camouflage, mimicry, or bioluminescence to catch prey. Deep-sea anglerfish, with their glowing lures, can attract prey from meters away in pitch-black darkness. Other organisms produce sudden flashes of light to confuse predators or communicate with potential mates. Each adaptation demonstrates a finely tuned balance between survival and predation, shaped by millions of years of evolution in isolated extreme environments. Reproduction in isolation presents additional challenges. In deep trenches and caves, encounters with potential mates are rare, driving unique reproductive strategies. Some species are hermaphroditic, ensuring that any meeting can lead to reproduction. Others, like certain anglerfish, have parasitic males that permanently attach to females, providing sperm for life. These adaptations guarantee that life can continue even in sparsely populated regions, highlighting the ingenuity of evolution in maintaining species survival under extraordinary conditions. Human exploration of these hidden ecosystems has expanded dramatically in recent decades, yet the majority remains unexplored and inaccessible. Advanced submersibles, remotely operated vehicles, and autonomous underwater drones allow glimpses of these alien worlds. But each expedition reveals more mysteries than answers. Scientists have discovered new species at astonishing rates, often in environments where life was previously thought impossible. Every observation reminds us of the ocean's vastness and the limitations of human knowledge. These hidden ecosystems are not only biologically fascinating, but also offer insights into Earth's evolutionary history. Many organisms found in deep sea caves, trenches, and hydrothermal vent systems resemble ancient species, providing a living window into past ecosystems. Studying these life forms helps scientists understand how life may have originated and adapted over geological timescales. Moreover, the extreme adaptations of these organisms inform astrobiology, offering clues about the potential for life on other worlds, such as the subsurface oceans of icy moons or distant exoplanets with hostile environments. Finally, a delicate balance in these ecosystems emphasizes the importance of conservation as human activity reaches deeper into the ocean. Through fishing, mining, and pollution, these fragile communities are increasingly at risk. Protecting these habitats is essential not only for preserving biodiversity, but also for maintaining the ecological processes that support life throughout the planet. Imagine drifting silently above these hidden realms, surrounded by alien landscapes, bizarre creatures, and life forms that thrive against seemingly insurmountable odds. Let the mind absorb the subtle currents, the faint glows, and the constant interplay of survival strategies. These hidden ecosystems remind us of the ocean's majesty, its mystery, and the resilience of life that continues to adapt in the darkest, most secluded corners of our planet. As we descend even further into the mysterious depths of the ocean, the hidden ecosystems reveal layers of complexity that defy imagination. These environments are not merely isolated pockets of life, they are dynamic, interconnected networks, where geological, chemical, and biological processes converge to create conditions that sustain remarkable forms of existence. Every crevice, trench, vent, and cave represents a finely tuned system, where survival depends on adaptability, cooperation, and resourcefulness. One of the most striking aspects of these ecosystems is bioluminescence. In the absence of sunlight, many deep-sea organisms have evolved the ability to produce their own light, creating a spectacular display of flickering and glowing patterns. From the tiny glowing plankton to the predatory lanternfish and anglerfish, bioluminescence serves multiple functions: attracting prey, confusing predators, communicating with mates, and even camouflaging against faint ambient light from above. This adaptation exemplifies the ingenuity of life in extreme environments, where every survival advantage is crucial. Hydrothermal vents continue to captivate scientists with their unique chemical and thermal gradients. The water emerging from these vents can reach temperatures exceeding 400 degrees Celsius. Yet life thrives in these scalding conditions. Microbial mats cling to the vent surfaces, converting chemical energy into sustenance for larger organisms. Tube worms, which lack mouths and digestive systems, rely entirely on symbiotic bacteria that inhabit their tissues. The balance between extreme heat, chemical abundance, and the surrounding cold creates microhabitats where life flourishes in ways that seem almost impossible. Deep sea trenches present a different challenge: extreme pressure at depths of over 10,000 meters. The crushing weight of the water above can exceed 1,000 times the pressure at sea level. Organisms living here have evolved bodies that are flexible, often gelatinous, allowing them to withstand these conditions. Cellular structures are reinforced, and metabolic processes are adapted to function efficiently under pressure. Many species have slow growth rates and extended lifespans, enabling them to survive in environments where food is scarce and reproduction opportunities are infrequent. Underwater caves, with their maze-like passages and total darkness, are another marvel of adaptation. Fish, crustaceans, and worms that inhabit these caves rely on enhanced sensory organs, antennae, lateral lines, and chemosensory systems to navigate and find food. The isolation of these caves often leads to endemism, with species evolving independently from their surface relatives. This evolutionary experimentation results in organisms that appear alien: translucent bodies, elongated appendages, or specialized feeding mechanisms that allow them to exploit the scarce resources. Available cold seeps where methane and other chemicals slowly escape from the seafloor. Support ecosystems that are equally fascinating. Mussels, clams, and polychaete worms dominate these regions, forming dense colonies that provide shelter and sustenance for other organisms. Chemosynthetic bacteria form the backbone of the food web, demonstrating that life can thrive without sunlight, relying instead on the chemical energy stored in the earth itself. These communities challenge our assumptions about the requirements for life and highlight alternative strategies for survival. Predation and defense strategies in the deep are particularly inventive. Some species produce toxins, others display startling bioluminescent flashes, and some even mimic surrounding features to remain invisible. Deep-sea anglerfish use luminescent lures to attract prey, while squid may release glowing ink to confuse predators. Each adaptation reflects the intricate balance of survival in an environment where mistakes are costly and opportunities are limited. Reproduction in these hidden ecosystems is equally remarkable. In sparsely populated regions, species have evolved unique strategies to ensure continuity. Hermaphroditism, parasitic male attachments, and synchronized spawning events all demonstrate the creativity of evolutionary solutions. Life persists against the odds, revealing an astounding capacity for adaptation. The interconnectedness of these ecosystems extends beyond the immediate environment. Nutrient flows from one habitat support life in another, creating a vast network that sustains the deep ocean. Even the simplest microbial communities can influence the structure and function of larger ecosystems, illustrating that every organism, no matter how small, plays a role in maintaining balance. As we traverse these alien landscapes, imagine the quiet hum of the deep, the slow drift of sediment, the faint glows of bioluminescent creatures, and the astonishing diversity of life forms that persist where humans rarely venture. The deep ocean is a testament to resilience, creativity, and the relentless drive of life to adapt, evolve, and endure in environments that challenge every expectation. Exploring the deep ocean is one of the most formidable challenges humans have ever undertaken. Despite advances in technology and centuries of curiosity, we have only begun to scratch the surface of these mysterious depths. The ocean covers more than 70% of our planet, yet more than 95% remains unexplored. The reasons for this are both physical and technological, rooted in the extreme conditions of the deep and the limitations of our current equipment. The first challenge is pressure. As we descend into the depths, the weight of the overlying water increases dramatically. At a depth of just 1 kilometer, pressure exceeds 100 times the atmospheric pressure at sea level. By the time we reach the Mariana Trench, the deepest known point in the ocean at nearly 11 kilometers, pressure is over 1,000 times greater than on the surface. This immense force can crush submersibles, destroy delicate instruments, and pose severe risks to human life. Engineers must design vessels with reinforced hulls, pressure-resistant materials, and intricate safety systems to withstand such conditions. Even with these precautions, every descent carries inherent risks. Temperature presents another significant obstacle. In many parts of the deep ocean, water temperatures hover just above freezing. Simultaneously, hydrothermal vents release water at hundreds of degrees Celsius, designing instruments that can withstand both extremes. Or operate in environments with rapidly shifting temperatures is a technical marvel. Electronics, cameras, and sensors must be insulated, cooled, or specially adapted to function reliably. And even small malfunctions can render an entire mission unsuccessful. Communication is also a formidable problem. Radio waves, the primary medium for wireless communication on land, cannot penetrate water beyond a few meters. As a result, deep-sea explorers rely on acoustic signals, fiber optic cables, or pre-programmed autonomous vehicles. Acoustic communication is slow and prone to interference, and even the fastest methods introduce delays, making real-time control of submersibles challenging. Pilots and scientists must often rely on autonomous navigation and pre-planned routes, which increases the complexity and risk of every mission. Visibility is another obstacle. Sunlight only penetrates a few hundred meters into the ocean, leaving the vast majority of the deep in total darkness. To observe these environments, submersibles and remotely operated vehicles (ROVs) carry powerful lights. But these can disturb sensitive organisms or alter natural behaviors. Cameras must be sensitive enough to capture subtle details without overwhelming the environment with artificial illumination. Bioluminescent organisms, which rely on darkness for survival, may be temporarily blinded or startled, potentially changing the very behaviors scientists aim to study. Access to the deep ocean is also physically limited. Even the most advanced submersibles and ROVs can only descend for hours or days at a time before needing to return to the surface for resupply, maintenance, or data retrieval. This constraint limits the scope of research, particularly for long-term ecological studies. Autonomous underwater vehicles, AUVs, can extend exploration, but they still face the challenges of power, navigation, and endurance. Another major challenge is the sheer vastness of the oceans. The deep sea is not a single uniform environment. It consists of trenches, abyssal plains, seamounts, vents, cold seeps, and canyons, each with unique topography and ecosystems. Mapping these areas requires high-resolution sonar, satellite positioning, and extensive planning. Even with modern technologies, only a tiny fraction of the seafloor has been mapped in detail. Many regions remain completely uncharted, hiding unknown species, geological formations, and chemical processes. Environmental conditions in the deep are highly variable. Currents, sedimentation, and chemical gradients can change over short distances, creating microhabitats that may not be detected without precise instruments. Scientists must design experiments and monitoring equipment that can adapt to these fluctuations, often relying on complex arrays of sensors and sample collectors. Human presence in the deep ocean is inherently limited by physiology. While submersibles can protect humans from pressure and cold, extended periods in these confined spaces pose psychological and physical challenges. Isolation, limited mobility, and the inability to access fresh air or exercise can affect cognitive function and overall well-being. Consequently, many deep-sea missions rely on unmanned or semi-autonomous vehicles. Leaving humans to observe remotely, scientific understanding of deep-sea ecosystems is further complicated by fragility and sensitivity. Many organisms are highly adapted to stable conditions, and even minor disturbances can cause mortality or behavioral changes. Sampling techniques must be precise, avoiding harm while still collecting meaningful data. This balance between exploration and preservation requires careful planning, innovation, and respect for the unknown. Despite these challenges, humans continue to push deeper into the ocean, driven by curiosity, scientific inquiry, and the potential for discovery. Each expedition uncovers new species, unusual behaviors, and insights into geological and chemical processes that shape our planet. From hydrothermal vents supporting chemosynthetic communities to deep trenches harboring previously unknown creatures, every dive expands our understanding of life on Earth. Technological innovations have accelerated exploration. Modern submersibles feature advanced robotics, high-definition imaging, and sophisticated sensors capable of measuring pressure, temperature, salinity, and chemical composition simultaneously. Data collection has become more automated, allowing scientists to process enormous volumes of information quickly and efficiently. Artificial intelligence and machine learning are increasingly integrated, identifying patterns, anomalies, and species from complex datasets. Yet, for all our progress, more than 90% of the deep ocean remains unexplored. Each journey into these uncharted realms raises more questions than it answers. What adaptations have evolved in the most isolated trenches? How do deep-sea ecosystems interact across vast distances? What unknown chemical and biological processes are taking place beneath kilometers of water? The mystery remains tantalizingly out of reach, compelling scientists and explorers to continue their pursuit. The challenges of deep-sea exploration highlight not only the difficulty of reaching these hidden worlds, but also their profound importance. The deep ocean influences global climate, regulates biogeochemical cycles, and sustains biodiversity critical to planetary health. Understanding these processes is not merely an academic pursuit, has practical implications for fisheries, climate prediction, and even medicine. As novel compounds and enzymes are discovered in these extreme environments as we navigate the uncharted depths, we are reminded of the fragility and resilience of life, the ingenuity required to survive in extreme conditions, and the vastness of a world that remains largely invisible to human eyes. Each obstacle we overcome is a testament to human determination and technological ingenuity, yet the ocean continues to guard its secrets, urging patience, curiosity, and humility. As we continue to examine the challenges of exploring the deep ocean, it becomes clear that technology alone is not enough. While submersibles, remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, have revolutionized our ability to venture into the abyss, the ocean's extreme conditions continually push the limits of these machines. Salt water is highly corrosive. Pressure can deform even the strongest materials, and temperatures vary dramatically near hydrothermal vents or in cold abyssal zones. Designing equipment that can operate reliably under these conditions requires not only advanced engineering, but also constant innovation and adaptation. Navigation in the deep ocean is another formidable challenge. GPS signals, which are essential for positioning on land or near the surface, cannot penetrate water. As a result, deep-sea vehicles rely on acoustic positioning systems, inertial navigation, and onboard sensors to maintain orientation. Even the slightest error in navigation can result in vehicles drifting off course, missing critical areas, or even colliding with underwater structures. Mapping the ocean floor requires repeated surveys and careful triangulation, often over weeks or months, to ensure accuracy. Energy supply is a limiting factor for extended missions. Submersibles and AUVs rely on batteries or tethered power sources, and long-duration dives require meticulous energy management. Every maneuver, light, and instrument consumes precious power, forcing mission planners to prioritize objectives and optimize vehicle operation. Innovations in battery technology, energy-efficient propulsion systems, and renewable energy integration, such as using temperature gradients or pressure changes, are critical to expanding our ability to explore. Deeper and longer communication with deep-sea vehicles remains constrained. Acoustic signals are the primary method, but these are slow and can be distorted by water conditions, temperature layers, and underwater topography. Delays in communication prevent real-time control in many situations, forcing operators to rely on pre-programmed instructions or semi-autonomous behavior. In areas where multiple vehicles operate simultaneously, signal interference can complicate coordination, requiring careful planning and advanced software to manage multiple missions. Concurrently, sampling and data collection present further difficulties. Many deep-sea organisms are delicate, adapted to extreme pressure, low temperatures, and complete darkness. Bringing them to the surface often results in death or structural damage, limiting researchers' ability to study them in detail. Precerating containers and specialized sampling techniques are being developed to preserve these organisms. But such methods are complex, expensive, and not always successful. Even sediment and water sampling require careful handling to prevent contamination or chemical changes that could alter scientific results. The physical terrain of the deep ocean adds another layer of complexity. The seafloor is far from uniform. It consists of steep trenches, jagged ridges, hydrothermal vent fields, and deep canyons. Navigating these regions requires highly maneuverable vehicles capable of precise movements, sometimes within meters of the seafloor or delicate ecosystems. Unexpected obstacles, such as rockfalls or dense sediment plumes, can damage equipment or disrupt scientific observations. This terrain also complicates mapping, requiring multiple passes and redundant systems to ensure accuracy. Environmental conditions, including currents and turbulence, challenge both human and robotic exploration. Deep currents can sweep vehicles off course or create hazards for tethered submersibles. Sediment clouds stirred by movement obscure visibility, while chemical gradients in the water can affect sensors and instruments. Engineers and scientists must continuously monitor and adjust for these conditions, balancing the need for data collection with the risk of disturbing fragile habitats. Human factors also contribute to the difficulty of deep-sea exploration. Pilots and researchers operating submersibles face intense psychological pressures, confined spaces, and prolonged isolation. The mental strain of watching hours of dark, featureless water, combined with the knowledge that a single error could endanger the mission, requires extensive training and resilience. Physical effects, such as changes in blood pressure, limited mobility, and reduced exercise, also challenge long-duration dives. Consequently, much of the exploration is conducted remotely, with humans observing from the safety of surface vessels. Funding and logistical constraints further limit deep-sea exploration. Each expedition requires significant resources. Vessels, crew, equipment, and maintenance are costly. Research priorities must be carefully balanced against available funding, and long-term studies are difficult to sustain. International collaboration is often necessary to access specialized vessels and expertise, but coordination across countries and institutions can be complex and time-consuming. Despite these obstacles, partnerships and technological advances continue to push the boundaries of what is possible. Scientific interpretation adds another layer of complexity. Data collected from deep-sea environments is often vast, diverse, and challenging to analyze. Understanding how physical, chemical, and biological factors interact requires interdisciplinary expertise. From marine biology and geology to chemistry, physics, and engineering, patterns are often subtle, and observations can be context-dependent, requiring repeated studies and cross-validation to draw meaningful conclusions. Yet each discovery, whether a new species, a chemical process, or an unknown geological formation, as a crucial piece to the puzzle of understanding the deep ocean. Finally, safety and ethical considerations are paramount. Deep-sea exploration involves risks to human life, delicate ecosystems, and even the integrity of scientific experiments. Ensuring safety for both crew and the environment requires stringent protocols, careful planning, and constant monitoring. Researchers must consider the potential impact of their activities, from physical disturbances to the introduction of foreign materials or organisms. Balancing the desire for discovery with responsibility and sustainability is a constant challenge, one that underscores the respect required when venturing into these largely uncharted and fragile environments. Despite these challenges, humanity continues to explore the deep ocean driven by curiosity, the potential for discovery, and the profound importance of understanding our planet. Each expedition, each dive, and each sample collected provides invaluable insight into ecosystems that have existed largely untouched for millions of years. The deep sea remains one of the last great frontiers on Earth, a world of wonder, mystery, and unending scientific intrigue. As we delve further into the challenges of deep-sea exploration, it becomes evident that even with advanced technology, the ocean remains one of the most inhospitable and mysterious environments on Earth. The very depth that captivates scientists also presents near insurmountable obstacles, requiring ingenuity, patience, and an unwavering curiosity to overcome. One of the most significant ongoing challenges is long-term observation. Many deep-sea phenomena occur over extended periods, from the slow growth of hydrothermal vent communities to the seasonal migrations of deep-dwelling organisms. Traditional expeditions, which often last only days or weeks, provide snapshots rather than continuous data. To address this, researchers have developed autonomous observatories and sensor arrays capable of monitoring environmental conditions, chemical changes, and biological activity over months or even years. These systems, however, face challenges of power, maintenance, and data storage, as well as the difficulty of retrieving collected information from extreme depths. Pressure, as discussed previously, continues to be a relentless adversary. Even the strongest submersibles are limited by the materials and engineering techniques available. Engineers constantly seek innovative alloys, composites, and structural designs to withstand crushing forces. But any new solution must be rigorously tested to ensure reliability. Failures can be catastrophic, and the margin for error is almost non-existent. The extreme pressure not only threatens vehicles, but also limits the ability to perform certain types of experiments or manipulations. Delicate instruments must be carefully protected and adapted to function precisely under these conditions. Temperature gradients in the deep ocean are another complex challenge. While the abyssal plains maintain near-freezing temperatures, hydrothermal vents emit water exceeding 400 degrees Celsius. Such extremes necessitate specialized instruments, capable of withstanding sudden changes in heat without compromising functionality. Thermally insulated enclosures, adaptive materials, and rapid response sensors allow scientists to monitor conditions without damaging equipment. Yet, the extreme thermal variation can still create unpredictable conditions, forcing constant adjustments. During missions, visibility remains a constant obstacle. In near total darkness, natural light is non-existent beyond a few hundred meters, requiring artificial illumination for any observation or recording. Lights must be sufficiently powerful to illuminate the environment, but subtle enough to avoid disturbing sensitive organisms or altering their behavior. Bioluminescent creatures, in particular, can be temporarily blinded or startled, creating challenges for accurately studying their natural interactions. Cameras and sensors must balance sensitivity, range, and exposure, often relying on multiple technologies to capture the full complexity of the deep sea. Environment-energy management is a critical consideration for extended missions. Submersibles, ROVs, and AUVs rely on batteries or tethered power sources, and energy conservation becomes paramount during long dives. Every maneuver, data collection effort, and lighting adjustment consumes valuable power, making efficient planning essential. Recent innovations in energy storage, such as high-capacity lithium-ion batteries and fuel cell technology, extend mission duration. But energy remains a limiting factor, particularly for deep, remote, or long-duration explorations. Communication with vehicles in the deep ocean is inherently limited. Acoustic signals, the primary method for transmitting information, travel slowly and are susceptible to distortion by environmental factors such as temperature, salinity, and underwater terrain. Real-time control is often impossible, requiring operators to rely on pre-programmed instructions or semi-autonomous behavior. This creates challenges for tasks that require fine motor control or immediate responses, such as collecting fragile specimens or navigating complex terrain. Mapping the seafloor continues to be a monumental task. High-resolution, sonar, multi-beam, echo sounders, and satellite data provide increasing accuracy, yet most of the ocean remains unmapped in detail. Uncharted regions may contain unknown species, unique geological formations, and unexplored ecosystems. The process of mapping requires multiple passes, careful calibration, and sophisticated software to integrate and interpret vast quantities of data. Even minor errors can lead to misrepresentations of terrain or missing critical habitats. Human factors play a significant role in deep-sea exploration challenges. The psychological strain of operating in confined, isolated spaces for extended periods combined with the knowledge of higher-risk conditions demands rigorous training and resilience. Physical effects such as limited mobility, changes in pressure on the body, and restricted access to fresh air, nutrition, and exercise further complicate human involvement. As a result, unmanned or remotely operated vehicles are increasingly favored. Though human observation and oversight remain essential for complex decision-making and interpretation, the deep sea is also remarkably fragile and sensitive. Many organisms are adapted to extremely stable conditions, and even minor disturbances can have significant ecological impacts. Sampling, vehicle movement, and artificial lighting must be carefully managed to avoid harming these ecosystems. Containers, specialized collection tools, and non-invasive observation techniques are used to minimize the impact on living organisms while still enabling scientific study. Researchers must constantly balance exploration goals with environmental responsibility, ensuring that the act of discovery does not inadvertently destroy the very ecosystems they seek to understand. Finally, the challenge of scientific interpretation cannot be overstated. Data collected from the deep ocean is vast, complex, and multidimensional. Understanding the interactions between physical, chemical, and biological processes requires interdisciplinary expertise and careful analysis. Patterns can be subtle, context-dependent, and subject to variability. Each observation, whether of an organism's behavior, a chemical gradient, or a geological formation, adds a piece to a massive, intricate puzzle. Interpretation demands patience, critical thinking, and often multiple expeditions to verify findings. Despite these myriad challenges, deep-sea exploration continues to yield remarkable discoveries, from bioluminescent species that defy our imagination to hydrothermal vent ecosystems that thrive without sunlight. Each dive reveals new insights about life, Earth's processes, and the potential for unknown resources. Technological advancements in robotics, materials, science, energy storage, and autonomous systems are progressively expanding our reach. The ocean's depths, while extreme and unforgiving, remain a frontier where human ingenuity, curiosity, and persistence are continuously tested. The deep ocean's mysteries are immense, and exploration is far from complete. Each expedition uncovers more questions than answers, prompting further inquiry and innovation. While the challenges of pressure, darkness, communication, navigation, and sensitivity are significant, they are surmountable with careful planning, advanced technology, and scientific dedication. The rewards of exploration: new species, ecosystems, chemical processes, and geological insights underscore the profound importance of understanding the largest, most mysterious habitats on Earth. As we descend further into the depths, a new world begins to unfold, a world entirely unlike the sunlit waters we are accustomed to. The deep ocean is home to an astonishing diversity of life, much of it still unknown to science, while only a small fraction of the ocean has been explored. The species discovered so far reveal an ecosystem both fragile and resilient, adapted to extreme conditions that would be inhospitable to humans. Life in the deep ocean is largely dictated by pressure, darkness, and scarce resources. Organisms have evolved to survive under crushing pressure, often hundreds of times greater than at the surface. Their bodies exhibit unique adaptations, including flexible structures, minimal skeletal support, and specialized cellular mechanisms to withstand extreme compression. Unlike surface animals, many deep-sea species do not rely on sunlight. Instead, they depend on the sparse nutrients drifting from above, chemosynthesis near hydrothermal vents, or predation of other organisms in the dark. One of the most striking adaptations is bioluminescence. Many deep-sea organisms produce their own light, whether to attract mates, lure prey, or communicate. From tiny shrimp to colossal squids, bioluminescent abilities vary in color, intensity, and pattern. This biological light show serves both practical and defensive purposes. In the pitch-black depths, a sudden flash can confuse predators or signal potential mates across vast distances. Researchers study these light patterns not only to understand communication, but also to gain insight into evolution in extreme environments. Predatory strategies in the deep ocean are particularly fascinating. Food scarcity drives creativity and efficiency. Some fish have enormous, expandable mouths to engulf prey larger than themselves. Others employ lures or mimicry, blending into the environment, to ambush unsuspecting victims. Many predators rely on highly sensitive senses, detecting vibrations, chemical signals, or faint traces of bioluminescence to locate prey in complete darkness. The interplay between predator and prey in this environment exemplifies the delicate balance of survival under extreme conditions. Hydrothermal vent ecosystems represent another unique corner of the deep ocean. Unlike sunlit ecosystems, these communities rely on chemical energy rather than photosynthesis. Bacteria capable of chemosynthesis form the foundation of these ecosystems, converting inorganic chemicals such as hydrogen sulfide into energy. These microbes, in turn, support a complex food web, from tube worms and clams to crabs and fish uniquely adapted to survive near superheated vent openings. Studying these systems provides insights into the origins of life, as some scientists hypothesize that life on Earth may have begun in similar environments, deep-sea corals and sponges, despite their apparent fragility, form critical habitats for numerous species. Unlike their shallow water counterparts, many deep-sea corals grow slowly, sometimes for centuries, providing stable structures in otherwise featureless abyssal plains. These habitats host a wide array of creatures from small crustaceans to juvenile fish, offering shelter and feeding grounds. Conservation of these ecosystems is vital, as their slow growth makes recovery from disturbances exceptionally difficult. Human activities such as deep-sea mining and trawling pose significant threats, emphasizing the need for careful management. The behavioral patterns of deep-sea creatures remain largely mysterious. Many species undertake vertical migrations, traveling hundreds or thousands of meters toward the surface at night to feed, only to return to the depths by day. This movement, often in synchronization with environmental cues such as temperature or nutrient availability, demonstrates the adaptability and complexity of these organisms. Observing these behaviors requires sophisticated technology, including remotely operated vehicles and time-lapse imaging, as human presence alone can disrupt natural activities. Reproduction in the deep ocean is another area of remarkable adaptation. Due to sparse populations and vast distances, many species have developed unique strategies to ensure survival. Some exhibit hermaphroditism, while others produce specialized eggs or larvae capable of surviving extended periods without food. Certain species, such as the deep-sea anglerfish, have evolved extreme sexual dimorphism, with tiny males permanently attaching to females to guarantee reproductive success. These adaptations reflect the intricate balance between scarcity, survival, and reproduction in one of Earth's most unforgiving habitats. Symbiotic relationships are also a hallmark of deep-sea life. Organisms often rely on one another for nutrition, protection, or habitat. For instance, some shrimp live among the tentacles of anemones, gaining shelter while providing the host with food scraps. Fish and microorganisms form mutualistic relationships, with bacteria breaking down chemicals that the host cannot process. These partnerships illustrate the interdependence of species in an environment where isolation is common and resources are limited. Despite these remarkable adaptations, much of the deep ocean remains unexplored and countless species likely remain undiscovered. Scientists estimate that over 80% of deep-sea species are yet to be identified. And each expedition brings new surprises, from strange gelatinous creatures to previously unknown forms of microbial life. The challenges of studying these organisms are considerable: collecting samples without damage, maintaining pressure and temperature conditions, and observing natural behavior in situ. The rewards are profound. Each discovery not only enriches our understanding of life on Earth, but also inspires new questions about biology, evolution, and the resilience of life in extreme conditions. Understanding the hidden life of the deep ocean also has practical implications. Many deep-sea organisms produce unique chemical compounds with potential applications in medicine, biotechnology, and environmental science. Studying their survival strategies may inform innovations in materials, science, robotics, and energy efficiency. Additionally, insights gained from these extreme ecosystems provide valuable analogs for astrobiology, helping scientists consider how life might exist on other planets or moons with harsh environments. The deep ocean is both alien and familiar. It challenges our assumptions about what is necessary for life, revealing creatures that thrive without sunlight, in extreme pressure, and in temperatures that would kill most surface-dwelling species. It reminds us of the vastness of our planet and the limits of our understanding, compelling us to continue exploring, documenting, and protecting this largely hidden world. As technology advances and human curiosity remains insatiable, the mysteries of the deep ocean will gradually unfold, offering a glimpse into a realm that is both beautiful and essential, alien and intimately connected to the Earth we know. As we continue to explore the hidden life of the deep ocean, it becomes increasingly clear that this environment is home to some of the most extraordinary and bizarre organisms on the planet. Many of these creatures exist in a delicate balance, perfectly adapted to an ecosystem that operates under extreme conditions of pressure, cold, and darkness. While we have discovered a fraction of these species, each expedition uncovers more surprises that challenge our understanding of life itself. 1. Striking characteristic of deep-sea life is its adaptation to darkness. With sunlight unable to penetrate beyond a few hundred meters, vision becomes almost irrelevant for many species. Instead, organisms rely on highly sensitive sensory adaptations. Some fish possess eyes that detect the faintest glimmers of bioluminescence, while others have evolved entirely to sense movement, vibrations, or chemical cues in the surrounding water. In such an environment, perception becomes multidimensional, integrating signals that are imperceptible to humans. Bioluminescence continues to dominate survival strategies. Many creatures, from small crustaceans to large squids, produce their own light to communicate, lure prey, or avoid predators. Some species use intricate patterns of flashing lights to signal one another over vast distances, while others employ sudden bursts of illumination to confuse or scare away threats. Bioluminescence not only serves practical purposes, but also creates a visually stunning and otherworldly spectacle that researchers strive to capture without disrupting natural behavior. Feeding strategies in the deep ocean are incredibly diverse. The scarcity of food has driven evolution toward highly specialized adaptations. Some predatory fish possess enormous mouths and extendable jaws, allowing them to engulf prey larger than themselves. Others are ambush predators, relying on camouflage or mimicry to approach unsuspecting prey. The interplay between predator and prey reflects a delicate balance, with every adaptation optimized for efficiency in an environment where calories are scarce. Hydrothermal. Vent communities continue to reveal the resilience of life. These ecosystems thrive on chemical energy rather than sunlight, relying on chemosynthetic bacteria that convert chemicals like hydrogen sulfide into energy. Tube worms, clams, and shrimp form complex networks around these vents, creating a dynamic food web that supports life in a location that would otherwise seem inhospitable. Studying these communities provides crucial insights into life's origins and potential survival strategies beyond Earth. Deep sea, coral, and sponge structures serve as critical habitats for many organisms. Unlike the vibrant corals found in shallow tropical waters, deep-sea corals grow slowly and endure extreme pressures and cold temperatures. They provide shelter for a wide variety of species, from tiny crustaceans to juvenile fish, maintaining biodiversity in an otherwise featureless abyssal plain. Protecting these slow-growing ecosystems is vital, as human activities such as deep-sea trawling and mining can cause irreversible damage. The behaviors of deep-sea species are both fascinating and mysterious. Many engage in vertical migrations, moving hundreds or thousands of meters toward the surface under the cover of night to feed before returning to the depths at dawn. These migrations, synchronized with environmental cues, nutrient availability, and predator avoidance, reveal a level of ecological complexity that rivals terrestrial ecosystems. Capturing these behaviors requires sophisticated tools such as time-lapse photography, remotely operated vehicles, and sensors capable of withstanding extreme pressure. Reproduction in the deep ocean also presents unique challenges. Sparse populations have led to extraordinary evolutionary strategies. Some species are hermaphroditic, ensuring reproductive success despite limited encounters with mates. Others produce eggs or larvae capable of surviving extended periods without food. The deep-sea anglerfish exemplifies one of the most extreme adaptations, tiny males permanently attached to females, providing a direct and lifelong reproductive opportunity. Such strategies highlight the intricate solutions life has developed to survive in isolation and scarcity. Symbiosis is another hallmark of deep-sea life. Organisms often depend on one another for survival, forming partnerships that range from protective relationships to nutritional exchanges. For instance, certain shrimp reside among anemone tentacles, gaining protection while helping the host by scavenging debris. Microbial partnerships with fish or invertebrates enable digestion of otherwise indigestible compounds. These intricate relationships underscore the interconnectedness of species in environments where solitary survival is challenging, despite the remarkable adaptations of deep-sea organisms. Vast portions of this ecosystem remain unexplored. Scientists estimate that more than 80% of species living in these depths are still unknown. Each discovery expands our understanding of life's possibilities, highlighting the extraordinary resilience and ingenuity of organisms that thrive without sunlight, under extreme pressure, and in near-freezing temperatures. Exploring these habitats continues to challenge researchers, pushing the boundaries of technology, biology, and imagination. The deep ocean also provides invaluable lessons for science and innovation. Studying unique biological adaptations can inspire advances in medicine, materials, science, and engineering. For example, bioluminescent mechanisms have applications in imaging and diagnostics, while pressurized structures inform deep-sea vehicle design. Understanding survival strategies in extreme environments also contributes to astrobiology, helping us speculate how life might exist on distant planets or moons. Ultimately, the hidden life of the deep ocean represents both a frontier and a mirror. It reveals the ingenuity of life on Earth while reminding us of the limits of human knowledge. Each organism, from the tiniest bacterium to colossal squid, plays a role in a complex, delicate ecosystem that remains largely mysterious. As technology evolves and exploration continues, we can expect to uncover further marvels, deepening our appreciation for one of the least understood yet most vital components of our planet. Descending deeper into the unexplored ocean, we begin to uncover even more astonishing aspects of the deep-sea environment. One of the most striking features is the extreme specialization of life forms, reflecting millions of years of evolution in isolation from sunlight and abundant food sources. Every creature we encounter is a testament to the power of adaptation, with body structures, behaviors, and survival strategies that seem almost alien. Many deep-sea organisms have developed extraordinary methods of locomotion. Some fish and cephalopods utilize fins and tentacles that allow them to move gracefully despite the density of the water and the crushing pressure. Other species rely on jet propulsion or undulating movements that conserve energy while allowing precise maneuvering in near complete darkness. Energy efficiency is critical, as food can be scarce and the cost of movement is high under extreme pressure. A major focus of study in recent years has been deep-sea gigantism, where organisms grow far larger than their shallow water relatives. Giant squids, colossal amphipods, and massive jellyfish exemplify this trend. Scientists believe that these unusual sizes may result from slower metabolisms, colder temperatures, and a scarcity-driven evolutionary arms race. Larger bodies may provide advantages in energy storage, reproductive success, or predation efficiency. These giants of the deep remain largely elusive, with most observations coming from rare encounters or deep-sea expeditions. Bioluminescence continues to reveal itself as one of the most sophisticated adaptations in the abyss. Not only do some creatures use it to hunt or evade predators, but others engage in intricate communication systems. Flashing sequences may signal mating readiness, territorial boundaries, or even warnings. The patterns of light can vary from simple glows to complex displays that are still being decoded by researchers. This natural light has inspired technological innovations in imaging, signaling, and scientific research. The relationships between species in the deep sea are equally compelling. Many organisms have formed symbiotic partnerships to survive in this harsh environment. For example, certain fish host bioluminescent bacteria to lure prey, while others rely on microbial communities to process chemical compounds they cannot digest alone. Even predator-prey interactions are unique. Some predators use deception, mimicry, or extended appendages to capture elusive prey in darkness, where eyesight is often useless. Hydrothermal vents remain one of the most fascinating ecosystems. These areas host life that thrives without sunlight, relying on chemosynthesis rather than photosynthesis. Communities around vents often feature species that are unique to these environments, including giant tube worms, vent crabs, and bacteria that harness energy from chemicals. Studying these vent communities gives researchers insight into the possible origins of life on Earth, as well as the conditions under which life could exist on other worlds. The scarcity of resources also drives unique reproductive strategies. Many deep-sea species are hermaphroditic, producing both eggs and sperm to maximize reproductive success. Some fish have evolved extreme sexual dimorphism, with males permanently attached to females to ensure mating in a vast and sparsely populated habitat. Others release eggs and larvae that drift for extended periods before settling, increasing the likelihood of survival despite limited food and mates. The deep sea floor, often described as an alien landscape, is home to ecosystems that depend on detritus falling from the surface. This marine snow of dead plankton, plant matter, and organic debris provides essential nutrition for scavengers and filter feeders. Crustaceans, sea cucumbers, and bottom-dwelling fish rely on this constant, albeit slow, delivery of nutrients. Studying these organisms reveals how life adapts to prolonged scarcity and illustrates The remarkable efficiency of deep-sea ecosystems. Despite the extraordinary discoveries, the deep ocean remains largely uncharted. Current estimates suggest that over 80% of deep-sea species are unknown to science, and the abyssal plains, trenches, and hydrothermal vent regions hold untold mysteries. Each expedition uncovers new species, behaviors, and ecological interactions, expanding our understanding of life on Earth and demonstrating the resilience of organisms that thrive in near-total darkness under extreme pressures. Human activity increasingly threatens these fragile environments. Deep-sea mining, trawling, and pollution have the potential to disrupt ecosystems that take centuries to recover. Conservation efforts are critical to preserving biodiversity and ensuring that future generations can continue to explore and learn from these remote regions. Protecting the deep ocean also provides insight into how life might adapt to extreme conditions elsewhere, offering a glimpse of what is possible in the vast universe beyond our planet. The hidden life of the deep ocean is both mysterious and vital, from the adaptations that allow survival under crushing pressure to the bioluminescent displays that illuminate darkness. These creatures reveal a world that is as beautiful as it is alien. Every new discovery reshapes our understanding of biology, ecology, and evolution. The deep ocean challenges our assumptions about what is necessary for life, showing that even in the harshest environments, life persists, adapts, and thrives. Exploring these depths requires not only advanced technology, but also a profound respect for the unknown. As research progresses, scientists continue to uncover unexpected behaviors, interactions, and adaptations, each contributing to a richer picture of the deep-sea ecosystem. The lessons learned here extend beyond the ocean, informing our understanding of biodiversity, sustainability, and the remarkable adaptability of life itself. The deep ocean reminds us of the vastness of our planet and the limitations of human knowledge. Every dive, observation, and discovery offers a glimpse into a world that remains largely invisible, yet is essential to the balance of life on Earth. By studying and protecting these ecosystems, we not only expand our scientific understanding, but also preserve a vital part of our planet's natural heritage, ensuring that the hidden life of the deep ocean continues to inspire wonder, curiosity, and respect. Exploring the deep ocean is one of humanity's greatest challenges, requiring cutting-edge technology to reach depths where pressure can crush conventional equipment and darkness stretches for miles. The vast majority of the ocean lies beyond the reach of sunlight, and navigating these regions demands both ingenuity and resilience. Modern deep-sea exploration relies on a combination of submersibles, remotely operated vehicles, ROVs, autonomous underwater vehicles, AUVs, and advanced sensors. Each of these technologies has revolutionized our understanding of the deep sea and continues to uncover life that was once thought impossible. Manned submersibles, such as the DSV Alvin, allow researchers to descend thousands of meters while directly observing the underwater environment. These vessels are engineered to withstand immense pressures, often with titanium or specially reinforced hulls. Within these submersibles, scientists can operate cameras, sampling tools, and navigation equipment, while remaining protected from the crushing forces outside. The ability to witness marine life firsthand provides insights that remote systems alone cannot achieve, such as behavioral observations and precise ecological interactions. However, manned submersibles are limited in range, endurance, and the number of people they can carry. To overcome these constraints, ROVs have become essential tools for deep-sea research. Controlled remotely from a surface vessel, ROVs are equipped with robotic arms, high-definition cameras, and instruments for collecting water, sediment, and biological samples. These vehicles allow exploration in areas too dangerous or too deep for humans, extending our reach to abyssal plains, trenches, and hydrothermal vents. ROVs also facilitate long-term monitoring, capturing time-lapse images and environmental data over months or even years. Autonomous underwater vehicles, AUVs, represent a newer generation of exploration tools. Unlike ROVs, AUVs operate without direct human control, following pre-programmed routes to collect data on topography, temperature, salinity, and chemical composition. Equipped with sonar, magnetometers, and other sophisticated sensors, AUVs can map the ocean floor with incredible precision. These devices are particularly valuable for surveying large, remote areas, revealing hidden geological structures, trenches, and undersea mountains that were previously unknown. High-resolution imaging technology has transformed our perception of deep-sea life. Ultra-sensitive cameras capable of recording in near total darkness allow researchers to document bioluminescent organisms and fragile habitats without disturbing them. Low-light imaging combined with infrared and thermal sensors provides additional dimensions of observation, capturing subtle movements, temperature variations, and interactions that were invisible to previous generations of explorers. By integrating imaging with environmental monitoring, scientists can study not only what lives in the deep sea, but also how these organisms respond to changes in temperature, pressure, or nutrient availability. Sampling in the deep ocean is another critical challenge. Collecting water, sediment, and biological specimens requires specialized tools that can operate under extreme pressure. Sediment corers, water samplers, and suction devices are carefully designed to ensure that samples remain intact during ascent. This is essential for studying chemical gradients, microbial communities, and the physical properties of deep-sea habitats. Additionally, molecular and genetic analysis of collected samples provides unprecedented insight into the diversity of life in these extreme environments. Communication with deep-sea equipment is often limited by the medium itself. Radio waves are ineffective underwater, forcing engineers to rely on acoustic signals, fiber optic cables, or tethered connections. Tethered ROVs, for instance, use physical cables to relay data in real time, while AUVs store information internally and transmit it upon surfacing. Advancements in underwater communication are crucial for extending operational range, enabling real-time monitoring and coordinating multiple vehicles simultaneously in complex environments. Pressure resistance remains the defining engineering challenge. At depths of 6,000 meters or more, the ocean exerts pressures exceeding 600 times that of the atmosphere at sea level. Submersibles, ROVs and AUVs, are designed with spherical or cylindrical pressure-resistant structures, ensuring that electronics, sensors, and propulsion systems continue to function reliably. Every material, seal, and connection must be rigorously tested, as even minor failures can result in catastrophic equipment loss. Navigation in the deep ocean presents its own set of difficulties. GPS signals do not penetrate water, so explorers rely on sonar mapping, inertial navigation systems, and acoustic positioning to determine location. Sonar, in particular, is invaluable for mapping terrain, detecting obstacles, and identifying potential points of interest such as hydrothermal vents, seamounts, or shipwrecks. Combining sonar with visual observation and environmental data allows researchers to construct detailed 3D maps of previously unknown regions of the seafloor. Energy supply is another limitation for long-duration missions. Deep-sea vehicles require power for propulsion, sensors, cameras, and communication systems. Batteries must provide consistent high-capacity energy while enduring extreme pressure and low temperatures. Innovations in lithium-ion and other high-density batteries as well as energy-efficient systems have significantly extended the operational capabilities of modern submersibles and AUVs. Some advanced designs even integrate renewable energy sources or use pressure-tolerant fuel cells to sustain longer expeditions. The integration of technology and scientific inquiry in deep-sea exploration represents one of the most remarkable collaborations of our time. Engineers, biologists, chemists, and geologists work together to design systems that can survive harsh environments, while providing valuable insights into the ocean's mysteries. Each expedition pushes the boundaries of knowledge, revealing life forms, geological formations, and chemical processes that challenge our understanding of biology and the Earth itself. Ultimately, deep-sea technology not only enhances our ability to explore but also serves as a model for innovation under extreme conditions. Lessons learned from submersibles, ROVs, and AUVs inspire developments in space exploration, medical devices, and materials science. By combining resilience, precision, and creativity, humanity continues to unlock the secrets of a world that remains largely unseen, offering a glimpse into the incredible complexity and beauty of the ocean's hidden depths. As we continue exploring the technologies that make deep-sea research possible, it becomes clear that interdisciplinary collaboration is the cornerstone of modern exploration. Engineers, marine biologists, oceanographers, and data scientists work closely to design vehicles and instruments that can survive extreme pressures while gathering accurate, meaningful data. Each mission requires meticulous planning, combining knowledge of marine environments, equipment capabilities, and research goals to ensure that both humans and machines can operate safely in such hostile conditions. One critical advancement in deep-sea exploration has been the development of adaptive robotic manipulators. These robotic arms allow scientists to collect delicate samples, such as fragile corals, soft-bodied invertebrates, or microbial mats, without damaging them. The precision of these manipulators is essential, as many deep-sea organisms are highly sensitive to changes in pressure, temperature, and handling. In some cases, robotic systems even mimic the movements of octopus tentacles, providing a combination of strength and flexibility to navigate tight spaces and retrieve samples that were previously inaccessible. Sonar technology has undergone remarkable evolution, enabling high-resolution mapping of seafloor topography. Multi-beam sonar systems emit multiple sound waves simultaneously, measuring the time it takes for each pulse to bounce back from the ocean floor. This technique allows researchers to construct incredibly detailed three-dimensional models of underwater landscapes, seamounts, trenches, hydrothermal vents, and underwater canyons that were once hidden are now charted with accuracy. That informs both scientific inquiry and navigational safety. Sonar also plays a crucial role in detecting marine life, including schools of fish or migrating whales, providing a non-intrusive way to observe behavior over vast areas. Environmental sensors are another vital component of deep-sea exploration. These instruments monitor temperature, salinity, pressure, pH, dissolved oxygen, and nutrient levels, giving researchers real-time data about the conditions that govern life at extreme depths. Some advanced sensors can even detect chemical signatures of hydrothermal vents, methane seeps, or other geological phenomena, providing insight into how energy and nutrients are distributed in the deep ocean. Data from these sensors help scientists understand how organisms adapt to extreme environments and how changes in ocean chemistry can impact biodiversity. Advancements in artificial intelligence, AI, and machine learning are transforming the way we interpret deep-sea data. AI algorithms can process enormous data sets collected by ROVs and AUVs, identifying patterns, classifying species, and detecting anomalies that human observers might miss. Machine learning models are also used to predict the locations of previously undiscovered habitats based on environmental parameters and known species distributions. This predictive power increases the efficiency of expeditions, allowing scientists to focus on areas with the highest potential for discovery. High definition imaging and low-light cameras have revolutionized how we visualize the deep ocean. Cameras capable of capturing clear images in near total darkness reveal the bioluminescent displays of marine organisms, from the rhythmic pulses of jellyfish to the intricate patterns of deep-sea squid. Time-lapse imaging allows researchers to observe slow ecological processes such as coral growth, microbial colonization, or sediment movement, which occur over weeks, months, or even years. These visual records are invaluable for understanding both individual organisms and the broader dynamics of deep-sea ecosystems. Another area of technological progress is the use of pressure-tolerant materials in submersible construction. Advanced alloys, ceramics, and composite materials allow vehicles to descend to unprecedented depths without compromising structural integrity. These materials not only protect electronics and life support systems, but also reduce the overall weight of the submersible, improving maneuverability and energy efficiency. As materials science continues to advance, future submersibles may be able to explore even deeper regions of the ocean that remain untouched. Communication and navigation remain ongoing challenges. In the absence of GPS signals underwater, acoustic positioning systems provide precise location data for ROVs, AUVs, and manned submersibles. These systems rely on sound waves transmitted between surface vessels and underwater devices, allowing operators to track movements and coordinate complex maneuvers. Advances in acoustic technology also support real-time video feeds, sensor data transmission, and coordinated exploration of multiple vehicles, which is critical for large-scale mapping and ecological monitoring. Power management is equally crucial for prolonged deep-sea missions. Submersibles and autonomous vehicles rely on high-capacity lithium-ion batteries, fuel cells, and energy-efficient propulsion systems to operate for hours or even days. Energy conservation strategies, such as optimizing movement patterns or temporarily deactivating non-essential systems, extend operational life and reduce the risk of mission failure. Some cutting-edge designs even explore the potential for harvesting energy from ocean currents or thermal gradients, offering possibilities for near-continuous exploration in the future. Finally, the integration of all these technologies, robust submersibles, precise robotic arms, advanced sensors, AI, and reliable communication systems enables a holistic approach to deep-sea research. Scientists can not only observe and document life forms, but also understand the complex interactions between organisms, geological features, and environmental conditions. This comprehensive perspective transforms our knowledge of the deep ocean from a series of isolated observations into a dynamic, interconnected understanding of an ecosystem that is still largely mysterious. The ongoing development of deep-sea technology underscores humanity's determination to explore the unknown. Each expedition reveals previously hidden life forms, geological formations, and ecological processes, expanding our understanding of Earth's final frontier. By pushing the limits of engineering and science, we continue to illuminate the depths, revealing a world that is both alien and astonishing, a testament to the resilience and ingenuity of life on our planet. As we continue to examine the technological advancements that have enabled humanity to probe the deepest parts of our oceans, it is important to consider not only the vehicles themselves, but also the systems and methodologies that support exploration. The orchestration of a successful deep-sea mission involves meticulous planning, real-time data analysis, and a strong integration of multiple technologies working seamlessly together. Without these systems, even the most advanced submersibles or UVs would be limited in their capacity to reveal the hidden wonders of the deep ocean. One critical aspect is mission planning and simulation. Before any vehicle descends into the abyss, scientists and engineers use computer models to simulate conditions at target depths. These models account for water pressure, temperature, salinity, and currents, allowing operators to predict how equipment will behave and identify potential hazards. By simulating the mission in advance, researchers can optimize vehicle trajectories, sampling strategies, and energy usage, ensuring that each dive maximizes both safety and data collection. Efficiency, another key element, is data management and integration. Modern deep-sea exploration generates enormous amounts of information, from high-definition video and sonar readings to chemical analyses and environmental measurements. Efficient storage, retrieval, and processing of this data are essential for drawing meaningful conclusions. Cloud computing and specialized databases enable teams across the globe to access, analyze, and collaborate on these datasets. The integration of environmental data with visual and genetic information helps researchers construct detailed ecological models, revealing interactions and patterns that would otherwise remain hidden. Deep-sea navigation is another area where precision technology is indispensable. Because GPS signals do not penetrate water, explorers rely on a combination of inertial navigation systems, Doppler velocity logs, and acoustic positioning networks. These tools allow vehicles to maintain accurate positioning even in featureless, pitch-black environments. Accurate navigation is essential not only for mapping the seafloor, but also for revisiting specific locations, monitoring changes over time, and ensuring safe operation around delicate habitats or geological formations. Robotic and autonomous systems are now equipped with increasingly sophisticated sensors and AI algorithms. These systems can autonomously detect interesting geological or biological features, adjust their trajectory, and collect samples with minimal human intervention. Machine learning algorithms help identify organisms in real time, track their behavior, and even anticipate movements based on previous observations. This capability allows explorers to gather data more efficiently, reduce human error, and uncover patterns that may otherwise be overlooked. Life support systems and pressure-resistant materials continue to evolve. Manned submersibles rely on meticulously engineered life support systems to provide breathable air, remove carbon dioxide, and regulate temperature and humidity for extended periods. Meanwhile, pressure-resistant materials such as titanium alloys, syntactic foams, and advanced ceramics ensure that both manned and unmanned vehicles can operate at extreme depths without structural failure. The continuous improvement of these materials has enabled missions to reach trenches and canyons previously thought inaccessible. The application of remote sensing technologies extends exploration beyond direct observation. Sonar mapping, magnetometers, chemical sensors, and bioluminescence detectors allow researchers to study areas far larger than the range of a single vehicle. By combining these tools with predictive modeling, scientists can identify promising regions for further investigation, locate hydrothermal vents or cold seeps, and even detect the presence of unique or undiscovered life forms. These remote tools are particularly valuable for understanding large-scale ecological dynamics and biogeographic distributions. Advances in sampling techniques are equally remarkable. Robotic arms, suction devices, and corers are designed to operate under high pressure while gently collecting samples of sediment, water, and living organisms. Preserving the integrity of these samples is crucial for studying their chemical, genetic, and ecological properties. Innovations such as pressure-retaining containers and cryogenic preservation allow scientists to analyze specimens as if they were still in their natural environment, providing more accurate insights into physiology and behavior. Energy management remains a critical factor in deep-sea exploration. Vehicles must operate for hours or days, powering propulsion, sensors, cameras, and communication systems while enduring cold, high-pressure conditions. The use of high-capacity lithium-ion batteries, fuel cells, and energy-efficient propulsion systems enables long-duration missions, while innovative designs explore the potential for harvesting energy from ocean currents, thermal gradients, or pressure differences. Efficient energy management ensures that vehicles can complete their missions without interruption or loss of critical data. Finally, the synergy between these technologies highlights the broader significance of deep-sea exploration. Each dive contributes not only to our understanding of marine life and geology, but also to innovations that have applications in other extreme environments, such as space exploration, high-pressure manufacturing, and advanced robotics. The collaboration of diverse scientific disciplines, engineering expertise, and technological ingenuity transforms the challenge of deep-sea exploration into a testament to human curiosity and resilience. The technologies enabling deep-sea exploration do more than facilitate discovery. They redefine the boundaries of what is possible. Each descent into the abyss uncovers new species, ecological interactions, and geological phenomena, expanding our knowledge of the ocean's hidden depths. As innovation continues, these tools will allow humanity to probe regions of the ocean that remain largely mysterious, revealing secrets that have persisted for millennia and inspiring a deeper appreciation for the complexity and resilience of life beneath the waves. Life in the extreme depths of the ocean is a realm unlike any other on Earth. The conditions are harsh, with crushing pressures, near-freezing temperatures, complete darkness, and scarce nutrients. Yet, despite these formidable challenges, stunning diversity of organisms has adapted to survive, thrive, and even flourish in this seemingly inhospitable environment. Understanding how life persists in these extreme conditions provides invaluable insights into biology, evolution, and the resilience of life itself. At the deepest levels of the ocean, pressure increases by approximately 1 atmosphere for every 10 meters of depth. This means that organisms living at depths of 6,000 meters experience pressures exceeding 600 times the atmospheric pressure at sea level. To withstand such immense forces, deep-sea organisms have evolved unique structural adaptations. For example, many fish possess flexible cartilaginous skeletons instead of rigid bones, which prevents them from being crushed. Similarly, soft-bodied invertebrates, such as jellyfish and certain mollusks, rely on hydrostatic pressure to maintain shape and buoyancy, enabling them to move and hunt without expending excessive energy. Temperature presents another significant challenge. The deep ocean is typically just above freezing, ranging from 1 to 4 degrees Celsius. Life in these cold conditions requires specialized enzymes and cellular structures that remain functional at low temperatures. Many organisms produce antifreeze proteins to prevent ice crystal formation in tissues, while cell membranes are composed of unique lipid molecules that retain fluidity in frigid waters. Metabolic rates in these organisms are generally slower, conserving energy in an environment where food is scarce and sporadically available. In addition to pressure and temperature, the absence of sunlight defines life in the deep ocean. Photosynthesis, the primary energy source for surface ecosystems, is impossible. Instead, deep-sea life relies on alternative energy pathways, such as chemosynthesis. In hydrothermal vent communities, bacteria and archaea convert chemical energy from hydrogen, sulfide, methane, or other inorganic compounds into organic matter. These microorganisms form the foundation of complex ecosystems, supporting giant tubeworms, crabs, shrimp, and other vent specialist species. The relationship between chemosynthetic microbes and their hosts exemplifies the intricate interdependence that defines life in extreme habitats. Bioluminescence is one of the most striking adaptations of deep-sea organisms. Over 80% of life below 1,000 meters can produce light through chemical reactions within specialized organs called photophores. Bioluminescence serves multiple functions: attracting prey, deterring predators, communicating with potential mates, and camouflaging organisms against faint, ambient light. Some species, like the anglerfish, use bioluminescent lures to draw unsuspecting prey close enough to be captured. Others, like lanternfish, emit subtle flashes to coordinate schooling behavior. Or avoid predation. Food scarcity drives another set of unique adaptations. Many deep-sea species exhibit opportunistic feeding strategies. Predators often have enormous mouths and expandable stomachs, allowing them to consume prey larger than themselves when the rare opportunity arises. Turdivores, organisms that feed on the remains of other creatures, rely on marine snow-tiny particles of organic material drifting down from the surface. This slow, steady rain of nutrients sustains countless species, from microscopic crustaceans to large fish, illustrating the remarkable efficiency of energy recycling in these ecosystems. Symbiotic relationships are also common in extreme environments. In addition to hydrothermal vent communities, deep-sea organisms often rely on partnerships with bacteria to extract nutrients from unconventional sources. For instance, some mollusks host chemosynthetic bacteria in their gills, allowing them to thrive in sulfide-rich sediments that would otherwise be toxic. Such symbioses highlight the adaptive creativity that evolution employs to overcome environmental constraints. Movement and communication in the dark depths require innovation. Many deep-sea species rely on enhanced sensory organs, such as highly sensitive lateral lines, antennae, or eyes adapted to detect minimal light. Some creatures, like certain squid species, use color-changing chromatophores to signal to each other in near-total darkness. Others rely on vibrations, chemical cues, or bioluminescent flashes for communication, demonstrating a remarkable diversity of sensory adaptations suited to life far from the sun. Predation strategies are often extreme and efficient. Deep-sea predators must maximize the energy they extract from each encounter. The gulper eel, with its massive, hinged jaws, can engulf prey nearly twice its size, while the deep-sea anglerfish employs both stealth and bioluminescent lures. These adaptations illustrate a recurring theme in extreme habitats. Energy efficiency is paramount, and every aspect of morphology and behavior is shaped by the scarcity of resources. Reproduction in the deep sea can also be uniquely adapted. Many species exhibit highly specialized mating strategies to ensure reproductive success despite low population densities. For example, the anglerfish displays sexual parasitism, where the male fuses to the female, providing a constant source of sperm while receiving nutrients. Other species rely on broadcast spawning, releasing gametes into the water column in synchronized events to increase the likelihood of fertilization. These reproductive adaptations reflect the extraordinary ways life has evolved to persist in one of the most challenging environments on Earth. Finally, studying deep-sea life has implications far beyond marine biology. Understanding how organisms survive in extreme pressure, cold, darkness, and nutrient scarcity provides insights into potential life on other planets or moons, such as Europa or Enceladus. These studies also inspire biomimetic engineering, where nature's solutions to extreme conditions inform the design of resilient materials, energy-efficient systems, and robotics capable of operating in hostile environments. The extreme depths of the ocean are a testament to the resilience and creativity of life. Every adaptation, from bioluminescence to chemosynthesis, tells a story of survival against staggering odds. By studying these organisms, scientists not only expand our knowledge of Earth's biodiversity, but also illuminate the possibilities for life in worlds beyond our own, underscoring the profound interconnectedness of all living systems. As we continue to explore life in the extreme depths of the ocean, it becomes increasingly apparent that these habitats are not barren wastelands, but vibrant ecosystems teeming with specialized organisms. The adaptations that allow survival in such extreme conditions reveal not only the ingenuity of evolution, but also the hidden complexity of Earth's most remote environments. In this section, we will delve deeper into the physiology, behavior, and ecological interactions that define deep-sea life. illustrating the remarkable ways in which organisms thrive where few could survive. One of the most fascinating aspects of deep-sea life is the diversity of feeding strategies. While some species are active predators, others are scavengers, filtering microscopic particles from the water or grazing on microbial mats. In abyssal plains, for example, giant amphipods feed on marine snow, a steady drift of organic material from the surface. These scavengers often display remarkable endurance, surviving on limited food sources for months. Energy efficiency is essential. Every movement and metabolic process is optimized to conserve energy. This is why many deep-sea creatures move slowly, relying on stealth and patience rather than speed or brute force. Some species have evolved extraordinary morphological adaptations to cope with the scarcity of food and the extreme pressure of their environment. The Borelli fish, for instance, has a transparent head, allowing its tubular eyes to rotate and detect faint bioluminescent signals from prey. Similarly, gulper eels possess expandable stomachs capable of ingesting prey larger than themselves, a crucial advantage in an environment where meals may be rare. These physical traits are mirrored by chemical and biochemical adaptations, such as pressure-resistant enzymes and antifreeze-like proteins, which ensure cellular function in conditions that would destroy surface-dwelling organisms. Reproduction in deep-sea ecosystems is equally intriguing. Many species face the challenge of finding mates in vast, sparsely populated environments. To overcome this, some fish and invertebrates employ extreme strategies. The deep-sea anglerfish, for example, exhibits sexual parasitism, where tiny males permanently attach to females, becoming dependent for nutrition while providing a continuous supply of sperm. Other organisms release vast quantities of gametes, simultaneously relying on the currents to bring eggs and sperm together in a synchronized reproductive event. These adaptations reflect the critical importance of reproductive efficiency in environments where encounters are rare and every opportunity must be maximized. Symbiotic relationships are another hallmark of deep-sea ecosystems. Hydrothermal vents, cold seeps, and whale falls provide unique habitats where life often depends on cooperation between species. Chemosynthetic bacteria form the foundation of these communities, converting inorganic compounds into organic matter. In return, host organisms such as tubeworms or mussels provide protection and a stable habitat. This mutualistic relationship allows both parties to flourish in conditions that would otherwise be lethal. Such symbioses underscore the interconnectedness of deep-sea life, where survival often depends on cooperation as much as competition. The behavior of deep-sea organisms is also shaped by the extreme darkness of their environment. Bioluminescence is not merely an adaptation for predation or mating. It is a language of survival. Organisms use light to attract prey, distract predators, communicate with potential mates, and camouflage themselves against faint background illumination. For example, the cookie-cutter shark employs counterillumination, producing light on its underside to blend with the downwelling light, making it nearly invisible to predators or prey below. Similarly, certain squid species use rhythmic flashes of light to coordinate hunting strategies or confuse rivals, demonstrating a complex and often surprising behavioral ecology. Mobility and navigation present additional challenges. In the abyss, where landmarks are scarce, many species rely on mechanosensory systems, such as lateral lines, to detect water movement and pressure changes. Others use chemical cues or subtle vibrations to locate food, mates, or threats. For instance, may detect the faint bioluminescence of prey from several meters away, adjusting its position and ambush strategy with incredible precision. Some species also exhibit vertical migration, moving hundreds of meters nightly to access richer feeding grounds while avoiding predators, illustrating a sophisticated understanding of their environment that balances risk, energy expenditure. An opportunity, deep-sea ecosystems also highlight the role of microbial life in supporting complex food webs. Microbes thrive in sediments, hydrothermal vents, and cold seeps, performing critical roles in nutrient cycling and energy production. They decompose organic matter, fix carbon, and even facilitate the availability of essential minerals for higher organisms. This microbial activity forms the backbone of ecosystems, demonstrating that life at extreme depths is sustained not only by large, visible organisms, but also by microscopic communities that maintain ecological balance. Another remarkable feature is adaptation to chemical extremes. Deep-sea habitats often contain toxic compounds such as hydrogen sulfide, methane, or heavy metals. Organisms inhabiting these zones have evolved specialized biochemical pathways to detoxify or even utilize these chemicals for energy. Tube worms, clams, and certain bacteria convert sulfides into nutrients, turning what would be deadly conditions for most life into a thriving habitat. These chemical adaptations underscore the versatility and resilience of life in the deep ocean. Studying life in extreme depths has broader implications for our understanding of biology, evolution, and planetary exploration. Many adaptations observed in deep-sea species inspire biotechnological innovations, from pressure-resistant materials to antifreeze proteins for medical or industrial applications. Furthermore, exploring these extreme ecosystems provides valuable insights into the potential for life in extraterrestrial oceans, such as those on Europa or Enceladus. Understanding how life thrives in darkness, under immense pressure, and with limited energy resources broadens our conception of what life can be. In conclusion, extreme depths of the ocean are a testament to the adaptability and resilience of life. Each organism represents a complex interplay of morphology, physiology, and behavior tailored to survive in one of Earth's harshest environments. From the smallest microbial communities to the largest deep-sea predators, life in these habitats challenges our understanding of biological limits and continues to inspire curiosity, scientific inquiry, and a profound appreciation for the mysteries hidden beneath the waves. The most remarkable feature of life in the extreme depths of the ocean is the extraordinary range of ecological niches it occupies. Each habitat, whether abyssal plains, hadal trenches, hydrothermal vents, or cold seeps, presents its own set of challenges and opportunities. The organisms that inhabit these niches have evolved highly specialized adaptations that enable them to survive, reproduce, and even thrive. Despite conditions that would be lethal to most surface-dwelling life, one of the most fascinating ecosystems exists around hydrothermal vents, where mineral-rich, superheated water gushes from the seafloor. These vents are oases in a dark, nutrient-poor environment. Chemosynthetic bacteria use the chemical energy in vent fluids to produce organic matter, forming the basis of complex food webs. Tube worms, clams, and vent crabs host these bacteria, either internally or externally, allowing them to gain nutrients in an environment completely devoid of sunlight. This symbiosis illustrates one of the key principles of deep-sea survival. Cooperation and mutualism are often as vital as competition. The pressure at extreme depths shapes the physiology of nearly every organism. For example, deep-sea fish, such as the snailfish, which inhabits trenches at depths exceeding 8,000 meters, have gelatinous tissues and reduced skeletal structures, making them flexible enough to withstand immense pressure. These adaptations also extend to cellular processes. Proteins in these organisms are structurally different from their shallow water counterparts, allowing enzymes to function efficiently under conditions that would denature ordinary proteins. Even DNA repair mechanisms are often enhanced to cope with oxidative stress and radiation exposure in certain deep-sea environments. Reproductive strategies are equally unique. Scarce encounters between potential mates have driven the evolution of extreme strategies to ensure reproductive success. As mentioned earlier, Anglerfish males attach permanently to females. But other species exhibit synchronized spawning, releasing gametes in vast quantities to maximize the chances of fertilization. Many species also exhibit hermaphroditism, possessing both male and female reproductive organs, allowing them to mate with any encountered individual of their species. These strategies demonstrate that reproduction, like every other aspect of deep-sea life, is adapted to overcome environmental limitations. Feeding strategies in the deep ocean are diverse and fascinating. Predators, such as the gulper eel, can swallow prey larger than themselves, while scavengers, like amphipods, efficiently consume detritus drifting from the surface. Some species, including the fangtooth and viperfish, use bioluminescent lures to attract prey, while others, such as benthic crabs and sea cucumbers, process sediments to extract microscopic organic particles. The slow pace of life and low metabolic rates help organisms conserve energy, ensuring survival even when food is scarce. Bioluminescence continues to play a critical role in behavior and survival. Some organisms emit light continuously, while others flash or pulse in patterns to communicate, confuse predators, or coordinate hunting. For example, lanternfish use counter-illumination to blend into faint light from the surface effectively, hiding from predators below. In contrast, squid and other cephalopods may employ rapid bursts of light to startle prey or rivals, illustrating that bioluminescence is not just a survival tool but also a form of behavioral sophistication. Microbial life is foundational to all deep-sea ecosystems. Bacteria and archaea thrive in sediments, hydrothermal vent plumes, and cold seep environments. They perform essential roles in nutrient cycling, converting inorganic chemicals into bioavailable compounds for larger organisms. In hydrothermal vents, chemosynthetic microbes form dense mats, supporting entire communities of invertebrates and fish. Even in abyssal plains and trenches, microbial activity sustains a vast array of scavengers and detritivores, highlighting the importance of microscopic life in maintaining ecosystem function. Adaptation to chemical extremes is another remarkable feature. Hydrogen sulfide, methane, and other potentially toxic compounds are often abundant in vent and seep environments. Organisms such as clams, mussels, and tube worms have evolved internal symbiotic bacteria that metabolize these chemicals, turning toxins into nutrients. This ability not only ensures survival, but allows these organisms to exploit resources that would be lethal to most species, illustrating nature's ingenuity in transforming adversity into opportunity. Mobility and sensory adaptations are critical. In the pitch-black, high-pressure depths, many organisms rely on mechanoreception, detecting water movement and vibrations to locate prey or avoid predators. Chemoreception allows detection of chemical cues over long distances, while enhanced visual systems adapted to detect faint bioluminescence facilitate hunting and mating. These adaptations highlight the interplay between environmental challenges and evolutionary innovation, demonstrating that survival in extreme habitats requires both physiological and behavioral flexibility. Finally, the study of deep-sea life has profound implications for science and technology. Researchers learn from pressure-resistant proteins, antifreeze molecules, and metabolic efficiencies, inspiring new materials, medical treatments, and energy-efficient designs. Additionally, studying these extreme environments informs astrobiology, as scientists consider the potential for life on icy moons and distant exoplanets. If life can adapt to the crushing pressures, frigid temperatures, and complete darkness of Earth's deep oceans, suggests that life elsewhere in the universe might also emerge in extreme and unexpected ways. The extreme depths of the ocean, with all their mysteries, represent both a challenge and an inspiration. Life thrives in forms and behaviors beyond what many would consider possible, demonstrating adaptability, resilience, and the boundless creativity of evolution. Each organism, from microscopic bacteria to to giant deep-sea predators contributes to a complex, interdependent ecosystem. Studying these depths not only deepens our understanding of life on Earth, but also expands our imagination of what life could be beyond our planet. The vast, uncharted depths of the oceans have long fascinated scientists, explorers, and dreamers alike. Despite covering over 70% of Earth's surface, the oceans remain among the least explored regions on the planet. Modern exploration has revealed only a fraction of the complex ecosystems and geological formations that lie beneath the waves. Chapter 10 examines the technologies, methodologies, and innovations that have enabled humans to probe these hidden depths, revealing the remarkable ways in which we attempt to uncover the secrets of the deep. One of the most significant challenges in ocean exploration is the extreme pressure. At depths exceeding 10,000 meters, pressures surpass 1,000 atmospheres, enough to crush conventional submarines and equipment. Early explorers relied on simple diving bells, which allowed limited immersion but posed severe limitations in mobility and safety. The invention of deep-sea submersibles marked a turning point, providing humans the ability to descend thousands of meters while maintaining life support systems. The Trieste, which famously reached the Challenger Deep in 1960, demonstrated the feasibility of manned deep-sea exploration, paving the way for future missions and technological innovations. Robotic technologies have dramatically expanded our capabilities. Remotely operated vehicles, ROVs, allow scientists to explore depths that are unsafe or inaccessible for humans. Equipped with high-definition cameras, manipulator arms, and advanced sensors, ROVs can collect samples, map terrain, and monitor ecosystems in real time. Unlike manned submersibles, these machines can operate for extended periods, withstand extreme pressures, and venture into the most hostile regions of the ocean. Similarly, autonomous underwater vehicles, AUVs, are programmed to navigate complex underwater terrain independently, gathering data on temperature, salinity, chemical composition, and biological activity. Mapping the ocean floor has also been revolutionized by sonar technology. Multi-beam sonar systems emit sound waves and measure the time it takes for echoes to return, generating detailed maps of seabed topography. These maps reveal underwater mountains, canyons, hydrothermal vents, and vast abyssal plains, illuminating the geological processes that shape our planet. Coupled with satellite-based gravimetric data, sonar mapping enables scientists to predict the location of previously undiscovered features and identify areas of high ecological importance. High-pressure laboratories and pressurized materials are essential for studying deep-sea organisms. Collecting live specimens from extreme depths is not enough. Scientists must maintain them in conditions that mimic their natural environment. Innovations such as pressurized sample chambers and temperature-controlled storage allow researchers to study behavior, metabolism, and physiology, providing insights into adaptations that enable survival under crushing pressure and near-freezing temperatures. These technologies also facilitate experiments with chemical adaptations, bioluminescence, and reproductive strategies, expanding our understanding of deep-sea life. Communication and data transmission in the deep ocean present additional challenges. Radio waves are ineffective underwater, especially at extreme depths. To overcome this, researchers rely on acoustic communication, using sound waves to transmit data over long distances. Advances in underwater fiber optic cables and satellite relays now allow near real-time monitoring of remote sites, connecting researchers to submersibles and sensor networks in previously unimaginable ways. This connectivity enables collaborative exploration, faster analysis of samples, and immediate responses to environmental changes or discoveries. The integration of artificial intelligence and machine learning is transforming ocean exploration. AI algorithms can process vast amounts of sonar, video, and environmental data to identify patterns, classify species, and predict ecological changes. Machine learning models help scientists detect rare or cryptic species, monitor population dynamics, and track changes in habitats over time. This not only improves our understanding of the deep ocean, but also allows for more targeted exploration, optimizing resources and reducing the risk of missing critical discoveries. Exploration is not limited to technological innovation. Human ingenuity and perseverance remain central. Deep-sea expeditions often require meticulous planning, coordination, and adaptability. Unexpected challenges, from equipment failures to unpredictable currents, test the resilience of both machines and humans. The success of missions like the discovery of the Titanic wreck, the exploration of hydrothermal vent communities, and the documentation of previously unknown species demonstrates the power of combining technology with human curiosity and problem-solving. Scientific collaboration is also a cornerstone of deep-sea research. International efforts, such as the Census of Marine Life, bring together marine biologists, geologists, chemists, and engineers to create a comprehensive understanding of oceanic ecosystems. These collaborations ensure that discoveries are widely shared, analyzed, and applied to broader questions about biodiversity, climate change, and planetary health. Moreover, interdisciplinary approaches allow innovations in one field, such as robotics or materials science, to benefit deep-sea exploration, creating a feedback loop of knowledge and technological progress. The importance of environmental monitoring and conservation is increasingly recognized. Human activities, from deep-sea mining to climate change, threaten fragile ecosystems that are often poorly understood. Exploration technologies now serve a dual purpose. Not only do they uncover new knowledge, but they also provide the data necessary to protect and manage these ecosystems. By mapping habitats, monitoring species populations, and assessing environmental health, researchers can make informed recommendations to policymakers, ensuring that the deep ocean remains a vibrant and resilient part of our planet. Ultimately, the quest to explore the ocean is both a scientific and philosophical journey. Every expedition challenges our assumptions about life, adaptation, and the limits of human knowledge. From discovering new species to understanding the chemical and physical processes that govern deep-sea environments, exploration fosters a deeper appreciation for Earth's complexity and resilience. As technology continues to evolve, the potential for discovery grows, suggesting that we have only begun to scratch the surface of what lies beneath the waves. As we continue to delve into the realm of ocean exploration, it becomes clear that the boundaries of human knowledge are constantly expanding, shaped by both innovation and the innate curiosity that drives exploration. Despite centuries of observation, the oceans remain one of the least understood components of our planet. Each technological advancement not only allows us to reach previously inaccessible depths, but also transforms the way we think about life, geology, and ecosystems in extreme environments. One area that has seen rapid development is underwater imaging. High-resolution cameras, 3D mapping tools, and specialized lighting systems now allow scientists to document deep-sea environments with unprecedented clarity. These systems can capture the behavior of organisms in their natural habitats, reveal subtle geological formations, and even detect microbial mats on the seafloor. Advanced imaging also enables the creation of virtual reconstructions of shipwrecks, hydrothermal vents, and deep trenches, allowing researchers and the public alike to experience these otherwise invisible worlds in extraordinary detail. Another significant innovation is deep-sea sampling technology. Collecting biological, chemical, and geological samples is critical for understanding oceanic processes. Modern submersibles and robotic arms are capable of collecting delicate organisms without causing damage, preserving their natural state for laboratory analysis. Sediment cores, water samplers, And biogeochemical probes allow researchers to study chemical gradients, nutrient flows, and microbial activity across different layers of the ocean. These tools have revealed that even the most remote trenches and abyssal plains host complex chemical interactions that support entire ecosystems, reshaping our understanding of ocean chemistry. Pressure-adapted habitats for laboratory study are also pivotal. Maintaining deep-sea organisms at surface pressure would result in fatal damage. So specialized pressurized containers replicate the extreme conditions of their natural environment. These high-pressure laboratories allow scientists to observe feeding behaviors, reproductive cycles, and metabolic activity without compromising the health of the specimens. Studies of these organisms, proteins, enzymes, and cellular mechanisms offer insights into extreme adaptation and inspire technological solutions in fields ranging from medicine to materials engineering. Exploration has also relied on advanced sonar mapping to reveal underwater landscapes. Modern multibeam and side-scan sonar systems create detailed topographical maps, identifying underwater mountains, canyons, and vent systems that were once hidden from human knowledge. Sonar mapping not only facilitates navigation for submersibles, but also aids in the discovery of unique ecosystems and rare species. When combined with remotely sensed data from satellites, sonar provides an integrated view of ocean basins, enhancing our understanding of plate tectonics, seafloor spreading, and sediment deposition. The development of long-duration autonomous vehicles has revolutionized our ability to collect continuous data. These vehicles can patrol vast stretches of the ocean for weeks or even months, monitoring temperature, salinity, and currents. Equipped with sensors and data loggers, they can track biological activity, such as fish migrations or plankton blooms, and detect environmental changes that might indicate pollution, climate change effects, or natural disasters. Continuous monitoring provides researchers with data sets of unprecedented scale and resolution, revealing patterns that were previously invisible. Acoustic monitoring is equally vital in deep-sea research. Sound travels efficiently through water, making it an ideal medium for communication and observation. Acoustic arrays detect whale calls, map seafloor geology, and monitor underwater volcanic activity. Passive listening stations can detect seismic events or submarine landslides, providing both scientific insights and early warning capabilities. Additionally, acoustic telemetry allows researchers to track the movement of tagged animals across vast oceanic distances, revealing migration patterns and behavioral adaptations to deep-sea conditions. The integration of biotechnology and molecular tools has opened new frontiers. Environmental DNA, eDNA, allows scientists to detect the presence of species simply by analyzing water samples for genetic material. This technique is particularly useful in deep or remote areas where direct observation is difficult. Metagenomic analysis of microbial communities reveals previously unknown lineages and metabolic pathways, shedding light on how life thrives under extreme pressure, darkness, and nutrient scarcity. Such insights inform our understanding of evolution, adaptation, and the potential for life in extraterrestrial oceans. Exploration is not without its logistical and ethical challenges. Deep-sea missions are expensive, often requiring extensive planning, specialized equipment, and skilled personnel. The need to preserve fragile ecosystems while conducting research necessitates careful protocols and minimal limbic techniques. International regulations, such as the United Nations Convention on the Law of the Sea, guide exploration to ensure that human activity does not harm vulnerable habitats or exploit resources unsustainably. Balancing discovery with stewardship is a recurring theme in deep-sea science. Ultimately, the study of ocean exploration and technology highlights the intersection of human curiosity, engineering, and ecological responsibility. Every expedition expands the limits of our knowledge, revealing the extraordinary adaptability of life and the hidden complexity of Earth's largest ecosystem. From mapping uncharted seafloors to observing life forms adapted to extreme pressure and darkness, technology allows us to venture where humans cannot go unaided, uncovering secrets that reshape our understanding of the planet and inspire new generations of explorers. The exploration of the deep ocean is a testament to human ingenuity and the relentless pursuit of knowledge. Despite decades of research, the vast majority of the ocean remains unexplored, with mysteries hiding in its deepest trenches and shadowed abysses. The final part of this chapter focuses on the integration of cutting-edge technologies, interdisciplinary collaboration, and the forward-looking innovations that promise to further unravel the secrets of the underwater world. One of the most transformative advances in recent years has been the development of hybrid submersibles. These vehicles combine the strengths of manned exploration with the versatility of remotely operated systems. Scientists can pilot the submersible directly when hand observation is required, then switch to remote control for delicate or high-risk tasks. Hybrid designs also allow longer missions, as the vehicle can return to a support vessel for maintenance or refueling without abandoning its collected data. This flexibility has enabled research in areas previously considered too extreme or dangerous. Bioluminescence. Detection systems have revolutionized our understanding of deep-sea life. Many organisms produce light to attract prey, communicate, or evade predators. Advanced imaging and light-sensitive sensors now allow scientists to observe these natural light displays in real time, revealing complex behaviors and interactions. Bioluminescence has proven to be more widespread than previously thought, occurring across multiple taxa, from jellyfish and plankton to deep-sea fish and even some bacteria. These observations provide insights into ecological relationships and evolutionary strategies that are impossible to discern through surface-level studies. The role of satellite and aerial technologies in oceanography has also expanded. While satellites cannot directly observe the deep ocean, they can detect surface anomalies such as sea surface temperature, chlorophyll concentration, and ocean currents. These data inform researchers about underlying processes, including nutrient flows and large-scale ecosystem dynamics, coupled with AI-driven predictive modeling. Satellite information can guide submersibles and ROVs to areas of scientific interest, optimizing exploration and ensuring that resources are deployed efficiently. High-pressure laboratories on land remain critical for studying collected specimens. Maintaining conditions that mimic deep-sea pressures is essential for understanding the physiology of organisms adapted to extreme environments. These labs provide insights into metabolism, reproduction, and adaptation, as well as unique biochemical compounds with potential applications in medicine, industry, and biotechnology. For instance, enzymes from deep-sea microbes often function under conditions that would denature ordinary proteins, offering templates for industrial catalysts or pharmaceuticals. The advent of underwater sensor networks represents a new era in continuous ocean monitoring. Arrays of sensors placed strategically across the ocean floor collect data on chemical composition, seismic activity, temperature fluctuations, and biological presence. These networks enable real-time observation and rapid response to natural events like tsunamis or volcanic eruptions. Moreover, sensor networks allow longitudinal studies that reveal subtle environmental trends over months or years, providing critical information about climate change impacts, habitat shifts, and ecosystem health. Collaboration across disciplines has become increasingly important in ocean exploration. Marine biologists, geologists, chemists, engineers, and data scientists work together to analyze complex datasets, design innovative tools, and interpret observations. Interdisciplinary research ensures that discoveries in one domain, such as hydrothermal vent chemistry, inform studies in another, like microbial ecology. International partnerships expand access to funding, vessels, and expertise, creating a global network of researchers committed to uncovering the secrets of the deep. The ethical dimension of deep-sea exploration cannot be overlooked. Human activity in the ocean, from resource extraction to pollution, can disrupt fragile ecosystems. Conservation-minded exploration emphasizes minimal impact techniques, sustainable sampling, and careful documentation. Policies guided by scientific evidence help ensure that deep-sea habitats remain protected while enabling the study of their unique biodiversity. Ethical exploration balances the desire for knowledge with the responsibility to preserve these unseen worlds for future generations. Emerging technologies like machine learning, AI, and big data analysis are transforming how we process the immense quantities of information collected during deep-sea missions. Algorithms can detect patterns, classify species, and predict environmental changes faster and more accurately than humans alone. AI-driven simulations help model deep-sea ecosystems and predict the consequences of natural or human-induced disturbances. By integrating large datasets from sonar, imaging, and environmental sensors, researchers gain a holistic understanding of deep-sea dynamics. From microbial activity to the behavior of apex predators. Finally, the exploration of the ocean is as much about inspiration as it is about science. Discovering new species, witnessing extreme adaptations, and mapping previously unseen landscapes reminds humanity of the vastness and complexity of our planet. Each expedition challenges assumptions, sparks curiosity, and reinforces the connection between humans and the natural world. As technology continues to evolve, the boundaries of ocean exploration will expand, revealing secrets that challenge our understanding of biology, chemistry, and the very processes that shape our planet. Through the combined efforts of human ingenuity, technological innovation, and global collaboration, the oceans gradually yield their secrets. The journey is ongoing, with each mission revealing new mysteries and opportunities for discovery. The integration of advanced submersibles, robotic technologies, AI, and long-term monitoring networks ensures that the next decades will bring even greater insights into Earth's most enigmatic frontier. The deep ocean, once inaccessible and unknowable, is now a realm of ongoing discovery, illuminating the intricate interplay between life, geology, and the human pursuit of understanding.